Hey everyone, how are we doing? Oh no, you can't hear the music anymore. I gotta get this fixed up. I have to change it around. But yes, how is everyone doing? I can hear the music and it appears you can't hear the music. Austin, Texas. Yeah, well, let's check out Austin, Texas. I know the other UT with the Oh man, how is everybody doing? Can everyone hear and see me as per usual? It's always my great fear that I'm not broadcasting and you guys are like, Brian, we can't hear you, we can't see you. It happens once every 20 streams. So every once in a while it happens. Can hear you, not the music. Yeah. It's for some reason something's going weird with the Go XLR. I don't know if it's an update to it, but my Go XLR board in the background right here, like, will it show? Oh, it doesn't show it's playing the music, but this is my music button. And it's not connected for some reason. I have no idea what's going on, but I can hear it. You guys can't, so you guys don't get to hear the Nintendo music. But with that said, that's so weird. I don't know. But we have the test out. We have the Kahoot at 3 p.m. today. There'll be some questions on the Kahoot that are most likely on your test. It's funny when I'm writing these questions, and there's lots of multiple choice on the test. There's lots and lots of multiple choice. There's numeric entry too. It's numeric entry and multiple choice. It's about a 70-30 split. And when I'm writing these questions, I feel like I'm tricking people. Like, not on purpose. But I'm like, these are the ones people usually get wrong. And I try to point them out during lecture. Like, for example, I think I can give this one because I've talked about this a billion times. Let's hop over to it. Let's bring up a question. I'm like, when I was writing it last night, I was like, people are gonna get this wrong. Let's go. So, what? Man, this is data mining. 70-30%, 70% multiple choice, 70-30%, 70% multiple choice, 30% numeric entry. So it's more multiple choice than numeric entry. It's about that, I'd say. It's like 30 multiple choice. There's 30 questions total, and I wrote 40-ish questions. So there, you get a random assortment of questions. You get a random set of questions from it. So there's a high likelihood things you see, and the concepts from today's Kahoot will be on the test. So the concepts or the questions literally themselves. So it's everyone's test is randomized a good bit. Wait a minute, what's that? What did we say? Did we say random? What? You know what we're talking about with random right there, because that's all we do in statistics. We do randomness. It's all random. This right here, actually, this is a concept we need to know for the test. What is RMSE? What is RMSE? You know, Brad, we're just destroying it. 100,000 points. First person who correctly tells me what RMSE is. I don't care. We're doing it. We're going crazy right now. Who knows what RMSE is? Ooh, yeah. Tell me like I don't know what statistics is. Oh, Brad, I like Brad's answer right now. I like the new one. I like the new answer. Yes. Okay, wait. We're gonna divide up the points right here. We're dividing up the points. 25 for Emily, 25 for Brad, 25,000. 25,000 for Brad, Emily, Mila, and Grant. There we go. Okay, we did it. So is the oh wait. No, it's 20,000. Megan gets some points too. And James and Alex. Okay, so now it's 15,000 each. Okay, I think we're good with that. Okay, so we gave out 100,000 points and Nicholas. So it's let me point out a lot of the right things that were said right here, and good work on it all. We need to be like, okay, what is RMSE? Typical size of the error made by the regression model. Top tier answer right there. Great job. And then typical misses. Very good, concise answer right there. Like the typical miss the model makes. Uncertainty also I like too, because that's the word I use for any sort of standard error. So that's like a general. Does that make sense? Like uncertainty is a good answer, but it's general to any sort of standard error. Like I always say standard error is uncertainty. So what is this uncertainty in? It's uncertainty in the residuals. And then what is it literally? Emily's right. Emily has a very technical right answer right there. It is root mean squared error. So we literally take the error, which is the residual, we square it, we take the mean of that, and then we root it. And when you think about this, once again, we always point out, why do we root and square it? Because what would be the mean error? Oh, I didn't put this as a test question. Means I could write it. No, people might have taken the test. So you know what's not on the test right now. What would be the mean error? What would be the mean error? If we just did mean error, what would every model have as a mean error? what would every model have as a mean error? If we just literally took the mean error of every model, we just said, oh, let's just look at the mean error. We could do that. What would it have? If you just did the mean error, like if you didn't do RMSE, you just did for your models, every model had mean error. That's all it was. You didn't do root mean squared error. You just did mean error of every model. Just the way we mathematically make these models. Every model would have a mean error equal to 0. That's why we square it. Because sometimes you're a little bit low, sometimes you're a little bit high. Every model would just have a mean error of 0. Because if you look at like a linear model and the way it works, like sometimes the simplest examples really exemplify what we're trying to talk about here, is that if you were to have a linear model and you had points slightly below and slightly above, you would have some points and some points below and some points above. So your error is the residual, the actual minus the predicted, and you're going to have some points below and some points above. So when you look at this, if this line is the line of best fit, which we're going to pretend it is, Brian tried to do a good drawing right here. If you were to just add up these errors, like make a residual plot and just add up these errors, so here's your residual plot, as Brad, I think you mentioned earlier, make the line flat. So we just have the same sort of thing going on right here as though the line has just been made flat. And when we do this now, we can see right here that if we were, see I don't have enough low errors. Oh, we got to make it more theoretically accurate. Put that. Because all of these errors, if you just added them up by doing the plus and minus on them, all of these errors right here would add up to 0. But what are you going to do with these errors when you do root mean squared error? Every single error here will get squared. So every single distance you have will get squared, and then you're going to sum them up, and then you're going to take the mean of them. Well, that's what you do when you take the means. You add things up, and then you root the errors. And the reason you root the errors is because you don't want squared units. So you're going to do the error, that's the RMSE of E, and then you take the mean, root mean squared, no, we square it. We take the error, we square it. We take the mean, we take the root. It's hard doing it in reverse. It's like saying your ABCs backwards. So you can think this is root mean of the squared error. And error is just the residual in the model. And so kind of, some good theory stuff. And I like showing this because this is BAS 474. And some people, like, I was getting emails yesterday from people who were thinking about joining 474, said the class is full. So, I want to get more people in. I am teaching online, so there might be more seats. I'm like, I'll take as many students as they will put in the class. I do not control these things though. So it's a bummer. And I feel bad. I get a lot of emails from people saying like, hey, Brian, I want to join your class. And I'm like, I don't control that. I have no control over that. Streamlabs, good job, Streamlabs, million-point Streamlabs. You are on par, Streamlabs. And so the root mean square error here, which model do you think is the best? The models with the blue lines, the model with the yellow lines, the magenta line, the red line, the yellow line? Which models do you think are the best in here? Which models do you think are the best? Think of what root mean square error is. Think of what root mean square error is. We just said what it is. So which models are generally the best right here? Any ideas? The blue line, the yellow line, the red line, the green line. We've got a lot of lines to choose from here. If you come into 474 with this type of knowledge, you'll be good. Blue. Whoa, nope. Sorry. Flip it. Not the blue. Because what is RMSE? It's typical miss. So you'd want your typical miss to be very what? It's red. The red has the best models. And you want the red with the small regularization. We're not going to mention what regularization is right now. But these are the models with the smallest typical miss. If you just think of RMSE as typical miss, you want the smallest typical miss. Does that make sense right there? I wish it was orange Stevenson, 1,000-point Stevenson. I wish it was orange, but it's not. Unless... No, I don't think it is. I was trying to see where orange... I think orange is right there. I was trying to see if it crossed through. I was like, I might be wrong, but I'm pretty sure red's all by itself down here. And I don't know if I still have this model saved in here. Which model was this? Oh, it's going to be a GLM net. So I can check for a GLM net. Let's do one last thing right here, and then we'll talk about one more thing. We're doing a lot of review today. So, which GLM net is it? I'll be able to tell real quickly. Okay, good. It's this one. This is 125 models made. So this is I love that, right there, Tyler. Tyler, because you took 474, right, Tyler? So you can tell them we just made 125 different models, and this looks to be a different set of models than I made right here. So maybe it was the other. Let me look at the other GLM net I made. So this is in 320 right here. So I should not name things the same thing as the code. Yeah, here's 125. Oh no, there's more than 125, and this is the right set of models. And row. This is 231 models. So the RMSE with the highest value is the best. Lowest. Did I say reverse of that? The lowest RMSE is the best. The lowest RMSE is better. These are not RMSEs right here. These are the RMSEs right here. This is the mixing percentage, which is your alpha. Don't worry about that. Here's your regularization parameter, which is your lambda. Don't worry about that. Yeah, so these are not RMSEs. The RMSE is only on this scale. This is your alpha mixing percentage, which Tyler can tell you is your lasso ridge. And then this is your lambda, which is your regularization penalty, which controls for the bias variance trade-off. If you're 474, you don't worry. No one here's 474, but those are things that 474 should know. Like when I talk about alpha, lambda, lasso ridge, GLM net, all these things, they should be like, oh yeah, I know that stuff. But this is what's cool, and this is what I want to point out right here. All of these models right here, in regression, what we've been doing this semester, how many of these models have we been making? How many of these models have we been making? 1,000 points first person. How many of these models have we been making? It's crazy points today. It's wacky Wednesdays. Crazy points today. How many of these models have we been making? Oh, not the flattest. No, this is all we're comparing here is RMSEs of different models. So don't worry too much about this. The only thing you should know so far about this is RMSE is typical miss of the model. That's a huge thing. You need to know RMSE is typical miss the model makes when making predictions. We've been only making, I don't want to show the answer. How many models have we been making every time we make models? When we make a model, we just make how many models? Every time we make models, we only make 1,000 right there. Brad, great job. And Mila. We make one, and Nicholas and Emily. Say one right now, get those points. And Stevenson, get those points. Megan. So Jonathan, yes, we only make one. So guess what we did in 474, which is what's completely awesome. In 474, we didn't make one model. We made 231 models. We made 231 different models. And we're trying to make the model that has the best predictive power. And I could have made 1,000 models if I wanted. I could easily make 1,000 models. Just, it only takes but a moment to make 1,000 models. It would take a little more than a moment. But I guess, yeah, I could do a grid of 30. But it's so cool. It's one of the most fascinating things. Here, let me see. I'll show you really, really quick. Let me just show this, and then we're going to keep talking about review for today. With this, I'm thinking of which one has it open right here. Do I have the homework 10 open? There we go. What we are doing, yeah, perfect, is we're actually using, do you remember how we've seen GLM? Does everyone remember in our class seeing GLM? 1,000 points, what does any of that stand for? You probably know, you should know what LM stands for. Because, and people asked this early on, I'd write LM and they'd say, what does LM stand for? And then we should maybe know what GLM stands for. I think I have everything still loaded up, so we should generalize. Alex, nice job. Generalized linear model. That's exactly it right there. That's the GLM. And watch this. This looks like a lot of code, but, and then we need to take out the tune grid. And now that code runs. We got error in predictions. Is that just warnings or warning message? Looks like it did it. There it did. It worked. It worked. It just gave us some warning message, rank deficient. That means that the X's have probably some high degree of multicollinearity. You should know multicollinearity. Let's talk about that. What is multicollinearity? What is multicollinearity? This is review. We're just reviewing. We're talking about cool things for the future. I love talking about future things. But what is multicollinearity? Let's hear, Brian's going to start drawing some data here with a high degree of multicollinearity. What is multicollinearity? What is this idea of multicollinearity, and where does multicollinearity show up? What is multicollinearity and where does it show up? These are your values of I was making a small data set. So be writing these down as review. I'm dropping major hints today. Multi-collinearity refers to a situation in which two or more explanatories are... Alex, you are on fire. That's 5,000 points right there. And Philip, 5,000 also, because everything, if you put Alex and Philip's answers together, amazing. Perfect, just that is like the sandwich of perfect answers. Like Alex gave the cheeseburger and Philip gave the bacon. Not saying that's like the perfect burger, but you're like, oh, that just needs a little bacon right there. It shows up in large VIFs. Just perfect answer right there. So when we think about this, and I was doing the y as a trick right here, the relationship that the x's have with the y have nothing to do with multicollinearity. Multicollinearity only focuses in on your x's. So when you think about this right here, you could have a variable like x completely explains y, and that'll cause issues. But those two being correlated has nothing to do with each other. I mean, like the multicollinearity of it. There's nothing in this right now that tells you multicollinearity. What would tell you multicollinearity is something like this. You're going to see the multicollinearity there, and boop. Let's see. You're going to see there's an interesting small data set. We'll make this one completely random, or kind of random. Sure, that's pretty random. I don't think it's going to have a high degree of multicollinearity. Like, if you look at the relationship this x has with this x, it's going to be relatively random. Most of the variation is going to be by random chance. And then you could have another one right over here, which we'll put at 5, 4, 3, 2, 1. Oh, it's the same numbers. Why did I do that? 2. And you know what we can do? So let me see right here. We could find out the multicollinearity of this. There we go. Okay, so let's just put this right here. And we're going to write data frame, data.frame, and we're going to do y equals... And then when you do a concatenated vector of 1, 2, 3, 4, 5, and yeah, you guys can still see that. Good, perfect. And then we're going to put a comma right here. So we're way off the screen, comma. And then we're going to take this vector. Wait, we're going to just barely not be able to see that one. We'll look at that here in a moment. And then we're going to just copy, copy, copy. And then we're going to change the numbers to 1, 2, 3, 4, 5. That's the same for this x1. And then this x2. Will be that, and it's 1, 2, 3, 4, 5, 4, and then the y, the x3. See, there might be some issues because the x1 completely explains y, and that was 2, 2, 3, 4, 5. And I'm concerned about. Let me change this to like 9. Okay, good. The reason is I wanted to include the variables in the model, and I figure it won't make estimates. Where did I lose it to? Okay, so I did change one number. There. Where's that data frame I made? There it is. So with this data frame right here, I'm back on the screen, am I? Error with no default. What did I do? Oh, there we go. There was a comma there, and for those who want the code, there's code right there. And let's go right here, and let's make a model, linear model. We've got the data frame, so it's y tilde, and then we're going to do dot for all the variables. Data equals data frame. It works, good. We're going to look at the summary of it. And did we get estimates for everything? We did. Whoa. How about these variables right here? You know what's really interesting? All of these, the relationship they have are by random chance. If we had just done like x1 by itself, still by random chance. I wonder if... Okay, not by random chance. Cool, but will we get the other estimates? Okay, good. I think we did it. I think that's more interesting. Okay, I like this example now a lot. Okay, so what we have right here is we have a model, and x1 by itself, because this gets into multiple regression, x1 by itself explains a significant portion of the variation in y. It actually explains 92.6%. Now, this is a very small data set, but almost all the variation in y, just look at x1. Almost all the variation in y is explained by x1. But think about this. What does it mean in the multiple regression that these other variables in this multiple regression, all of these variables now are not significant? The r squared, oof. Ooh, we got so many things to talk about right here. Can I get them? Oh, good. It's on the screen. Good. There's so much to talk about right here. These variables are not significant in the model right now. Why? Why are these variables not significant in the model? Why are these variables not significant in the model? Any ideas? Why are these variables not significant? They don't do what right now? They don't do what? What do these variables not do that the X was originally doing by itself in the model? That's, yep, Mila, the second part. And Brad right there. They don't provide new information. They're redundant in the information they bring. And you can really see that with the way the data is created. If you look at the data, you can see the redundancy in the information. That you've got 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, and 2, 2, 3, 4, 5. They're redundant in the information, which means we're really going to see this show up in the variance inflation factor. The variance inflation factor can let us see. Literature says between 5 and 10 is bad. So there is a high degree of redundancy. And you could say that because this is 22, we've inflated the standard error of this one by about a factor of 5. This is 65. We've inflated it by a factor of about 8. And so if I look at the original linear model, so that's 0.5. We times that by 8. It's an estimate of how much we've inflated it by, but that's how much you've about inflated the standard error. So does this make sense right here? That these variables have high redundancy with each other, and then the model gets confused. Because think about this. When we look at what explains what, we could, think of Y as a pizza. I haven't used this example lately. Think of Y as a pizza. And if we ask, how much of the pizza does X1 get to eat? When we look at how much of the pizza does X1 get to eat, let's say X1 gets to eat 92% of the pizza. How much of the pizza does X2 get to eat? 91% of the pizza. How much of the pizza does X3 get to eat? 82% of the pizza. Wait a minute. Can you eat 90% of a pizza, then 90% of a pizza, then 80% of a pizza? Does that work mathematically for variables to do that? For variables to each eat this amount of this pizza? Because they're going to come in, they're going to say, I get 90%, the other one says, I get 90%, the other one says, I get 80%. You're like, okay, that's what we're going to do. Does that work? Does that work? Doesn't sound like it works to me. Like when your parents say, we made a pizza, and your brother says, I get 90%, you say, I get 90% too. It's actually 260% pizza, like right there, Mila right there. So that doesn't work. Now I am talking about the why, but think about what this means. The way in which the X's explain Y overlap. They don't bring with them new information. The information in the X's is redundant. It explains Y in the same way. So it deals with the redundancy in information in the X's, even though we're talking about how they explain Y. Because you can look at it as though the ways in which they explain Y is redundant, and that means the X's have redundant information with each other. The X's share overlapping information, and if they try to explain Y, they'll overlap in what they do. So this is what multicollinearity is. We could try to see what we could do. Hopefully, it's such a small data set. If we do X4 right here, we're going to cheat because we're going to do random uniform. And we should be able to do, there we go, 5 numbers with a min of 0 and a max of 5. What would it look like if you input, let's look at that. We got that next here. Let's see. Hopefully, we might not. Did we get an estimate of all these? Oh, no. We ran out of stuff. There we go. Now there's random. There's real randomness. And that should, but it's such a small data set. And we're going to look at the example. Good job. Oh, yeah, look at that. That's like the lowest VIF we can get. Let me get still with the YM. Let me take a look. What? Good job, Jonathan. Jonathan, 1,000 points right there. Thank you, Jonathan, for, hey, can you look at this example? I like that. Let's clean up the code right here. And let's see the change Jonathan made right here. What change did Jonathan make? Oh, he gave complete, so this right, oof, I see it. What will happen is, so let's see if Brian can get the theory right before we make the model. What degree of multicollinearity, just don't worry about the mathematics. What degree of multicollinearity is there? I guess I could show it. I didn't put it on the test. Hint, I didn't put it on the test. But what degree of multicollinearity is there between the x's right now? Like when I look at the x's, what degree of multicollinearity is there? And if Nitin was here, he'd talk to us a little bit about matrix algebra, because this is completely linear dependence. So Mila and other people, if you're like in mathematics, this is a linear algebra problem now with complete linear dependency with the variables. Yeah, this is like perfect multicollinearity, which is horrible. This is the highest degree of multicollinearity. Mathematically, with the multicollinearity right now, if you calculate the value of multicollinearity, what we'd get is 1 over 1 minus, and it's r squared sub I. What are all the r squared sub i's right now? What are all the r squared sub i's? All the r squared sub i's are 1. So you get 1 over 0. You might say, well, what is that? It's something that approaches infinity. So because if you think about values like 1 over 0.000001, that'd be 10, 100, 1,000, 10,000, 100,000. That'd be 100,000 right here. So this would be 100,000 right here. So you're getting numbers that approach. Infinity, which is not a good thing. You do not want infinite multicollinearity. And what does this mean? It means the model cannot make estimates for the variables. So just theoretically speaking, if I ask this model to now make estimates for these variables, it says I cannot. It creates what we call a singularity. And so here we go. It cannot literally use these because the information they bring is completely and utterly redundant. There's a complete redundancy in the information, and it's like, I'm going to eat 100% of the pizza, and someone else is like, no, I'm going to eat 100% of the pizza. And we're like, actually, in truth, right now, to make it very, very specific, I'm walking in and I'm saying, I'm going to eat 25% of that pizza. And then someone walks in and they say, I'm going to eat that exact 25% that you just ate. And you say, you can't. You bring nothing new at all. Like, but I want to eat 25.8% of the pizza. You're like, nope, can't do it. You do exactly the same thing as I do, and you do nothing. Does this make sense right here, what's going on with the multicollinearity between the x's? I could look at another thing right here. Makes sense. I like that right there. It's good review topics today. A lot of review. Let's do this. Let's do an influence plot. We haven't seen I'm thinking of topics we haven't seen in a while that are on the test. Oof, that's like the worst possible. And this would not go on the test. Even I would have a hard time being like, what's going on with this influence plot right here? So the coefficient of 1 would only work in this instance. Yeah, like I saw the coefficient was 1. I thought that was interesting. That's just due to like just how the data worked out. So the coefficient of 1 is the estimate. This model right here is pretty easy, right? It's y equals 1.2 plus 1x1. And I wonder why it is that. It's just mathematically it worked out that way. Like mathematically, I don't know if I have a good theory answer for why it did that. There we go. And we're running with this data right here, right? It's interesting it turned out that way. And the intercept of that right there. It's the 9 that throws it off, because the 9 is the thing that breaks the mold of the model and creates lower. Oh, one thing I didn't mention. Here we're going to go back to the data I created right here. And would it be because each variable in x1... nope, not because of that. Yeah, no, it's just the estimate of the differences between two otherwise identical observations in this model. So between two otherwise identical observations. So we could do a quick interpretation right here. Oh, I didn't make the model. Let me make the model. 2 seconds. Gotta grab the code that makes the model. Not that I can't type it out again. There we go. So, oh, wait. Is this the one that had the singularity? Did I not rerun the code? There we go. There, I didn't rerun the code. This model right here, very important that we talk about this, is this, would we say otherwise identical in this model, or would we not say otherwise identical? Would we say between two otherwise identical observations where, so like, would the otherwise identical be used for this model, yes or no? Would we use otherwise identical here? I've been dropping lots of hints for the test today. Would we use otherwise identical right here? Why or why not? Why or why not? And yes, we would. Why? We definitely would. And why would we? Why would we use otherwise identical? Why would we? The key is why, though. You might be like, oh, we always say otherwise identical. Yep, that's exactly it. We're comparing multiple x's right here. And so since it is a multiple regression, we say, but are otherwise identical. So anytime you have a multiple regression, you use the phrase otherwise identical. But if you have a simple linear regression, you would not use the phrase otherwise identical. It's just bad practice. It's like when I worked at Cheddar's and people were like, I don't want whipped cream. And I'd be like, and I was like, oh no. I mean, some people are going to get mad about that. Some people are like, I said no whipped cream. You'd be like, you just wipe it off and you just take the whipped cream off. No, I don't know. I've been thinking about that dessert we have at Cheddar's, the Cookie Monster. Man, I just want like fast food and I don't know. COVID's making me go crazy. So we have right here, this one right here is X1, and we have right here between two individuals who differ in their X1 by 1 unit, they're expected to differ in their Y by 1 unit. But with the person with the higher X1 is expected to have the higher Y. But with that said, I don't love this model because, let me do X4. I don't want you to see 1, I don't want you to get confused. 2 observations that differ in their X4 by 1 unit are expected to differ in their Y by negative 0.326, where the observation with the higher X4 is expected to have the lower Y. What is X4? Doesn't matter. It's just whatever X4 is, whatever its units are. And I want to show the influence plot again, because I feel like that's something we haven't talked about in a long time. Let's make a classic model right here. So we'll just do our classic model. We do have it? Oh, good. Got everything loaded up. Okay. So we're going to look at an influence plot right here. Whoop. There we go. And let's take a look. We have the influence plot. Okay, what's going on with this influence plot right here? I said I can remove things like this. What's going on with this influence plot right here? These points down here are what? These points all the way down here on the far left side are very what? These points all the way down here are very, very what? These points down here are very, very what? And as we go over here, especially once we reach right here, what's going on with this plot right here? What is going on with it? Yep, Grant, 1,000 points. And more specifically, close to the mean of the x's. So this has to deal with the amount of leverage something has, which is how close something is to the mean of the x's. Leverage is not something we really want for our points because it can cause undue influence. Something that has undue influence would have to have both high leverage and high what else? 1,000 points, who else knows? What are the 2 things points would need to have high influence? Things that have high influence would have high this and high this. They'd have to have high leverage and high what else? It's basically on here. It's like, follow along, see what you think. So these points are very close to the mean of the x's. It's like a guy who is kind of residuals, pretty much. The deleted studentized residuals. It's kind of residuals. I mean, if you have a big deleted studentized residual, you probably have a big residual. So deleted studentized residual is the idea of removing the point itself, standardizing its units, and looking at its residual. Like looking at the residual of a point that's been removed and we've standardized its distance. So the delete, yeah, sure. Let's show the graphic again. Let's show what a deleted studentized residual looks like visually. So whenever you make a line, the points will always pull the line towards it. So you can have right here a line, and maybe we've got data like this right here. And probably, yeah, it's going to look like this because that point is pulling the line through it. And it should, without that point, trying to make one, sure, here we'll do this. Okay, so if you look at this, we have a point that has high influence because it's going to pull the line towards it. But what do we do now? Is we take and we make a line without that point. So literally this red line right here, what we do is we go and we delete this point. Does that make sense? The red line is created from taking that point and just deleting it. Now we have a line without the influence of that point. So we say, okay, let's make a line without this point. So that point is pulling the model towards it. You delete it and you make a model. Whoops, wrong thing deleted. You delete it and you make a model without it. There we go. Yeah, one more try. Okay, that first line was my favorite. Okay, good. We got it back now. So now what you do is you take and you get the residual to the model. Like this is its residual. That's E for residual. That's the notation for residual. And this would be kind of like residual deleted. So that's the deleted residual. So you're always going to get a larger deleted residual than you are a residual. Now, what does it mean to standardize it? It's going to be turned into a t-score. So we could say like turned into t. Turned into a t. So when is something a large deleted studentized residual? If it's a t-score, which is basically a z-score, when is something a large deleted studentized residual? If it's basically t's and z's are basically the same thing, because student t is William Gossett, who worked on the t distribution. And so deleted studentized residuals are pretty much big when they're outside of what or what. Think of 68, 95, 68, 95. And it does it for every point for us. Yep. We'll never do this by hand. We'll never do it by hand. It's done for us. 2 standard deviations, exactly. And that's it right here. It's basically 2 standard deviations or standard errors, but it's still the idea of uncertainties. And you would see that pretty much all the points, 95%, are expected to fall within plus or minus 2 uncertainties. So when is a deleted studentized residual big? When it's outside of positive 2 or negative 2. And you can see we've got some ridiculously large ones right here. So you delete a point and the residual pretty much didn't change between the individual. If you delete the point, because this specifically deals with the x's relationships with the y, so the deleted studentized residual is more of an xy relationship, and leverage is more xx relationship. Outside of that range, Grant, great job. And so the deleted studentized residual deals with an x, or, well, if you get a multiple model, it'll be x's, but it more specifically deals with the xy, kind of how far are we off in our predictions. But the leverage only deals with x or the x's. So when you look at leverage down here on the bottom, this point right here has high influence. This point down here has high influence because it not only has a large deleted studentized residual, but it also has large leverage. So this right there, the E subscript D, is its large deleted studentized residual. And then this right here is its large leverage. If this, technically this is the mean of the x's. Let's make it very technical right here and draw it as perfect as we can. So to draw this as best we can, that's about the mean of the x's. And then leverage would go this way. The mean of the x or the x's is the least amount of leverage something can have. So this area right here, this green area I'm drawing, that green area right there is awesome, Dennis. Glad to hear that. That green area right there is this. That green area right here is things that have next to no leverage. So that green line I just drew is when things have about 0 leverage, which means they're at the mean of the x's. Now you might say, is that the mean of the x's? We'll just say it is for the drawing purposes. Here, wait, I'm gonna have a few more points. There you go, that's about the mean of the x's now, because that one's also pulling up the mean of the x's. And now the leverage this point has is defined by its distance from the mean of the x's. Now there is just one x, but you can see here that this has both. We're going to add a new highlighter here. This has both. Oh, look at that one, that looks nice. Has high leverage and has a high deleted studentized residual. So because of that, it's going to have undue influence. And the influence in this graphic is the size of the circle. So here's some points with very extreme influence because one, they have high leverage. This is the high leverage point. You don't need to know the equation for it. It's like 2 plus k something. I see it. I know like, oh, that's the high leverage equation. You don't have to calculate it anymore. I used to have to calculate when I was in school. When I was in school, we had to calculate the high leverage. So influence is a combination of leverage. Yep. Bingo. Yep. And if one of them is 0, it has to be 0. If you notice how small these points get, like if you have no, like look here at the 0, Like this point has crazy leverage, but you can barely see it. Like, is that a smudge on my screen? Maybe someone's wondering about that now. Is that a smudge? No, that's a point that has next to no influence. It is next to no influence because it has no deleted student isoresidual. So this point right here has no influence because it's like almost perfectly on the model. If we were to draw that conceptually over here, it's got to be something with very high leverage. And remember, I'm going to erase the red line. So this point right here, if it existed in our model, we'll draw it as the green dot, would be something way over here. Because that point right there, that green dot I just drew, is basically perfectly on the model, but it has high leverage. So let's look at that again. That little smudge on the screen, that tiny smudge, is almost perfectly on the model, and it has high leverage. So perfectly on the model is its distance right here from 0. It's almost perfectly on the model, but it has high leverage. And so when you look at that again, let's just see the model again. Perfectly on the model, but has high leverage. Perfectly on the model, has high leverage. Now, technically, here's the thing, though. This could also be it. That could also be that green dot. Because leverage can only be what? Think about what is Brian pointing out here. Leverage can only have a what value. Leverage can only have a what value. Leverage can only be, and here's the hint. Look, where do you think this starts? Leverage can only be what? Yep, exactly. Exactly, it's just your distance from the mean. So would that be, would the one out by, which one, Brendan, which one are you talking about? Oh, this one right here? Yes, Brendan, great job, 1,000 points, Brendan, you're exactly right. These right here have ridiculous leverage. These are the highest leverage points. Like these 2 points are the 2 furthest points out from the mean of the x's. These are the 2 furthest points out. Yeah, I know, right? No, Dennis, you have to hear things like 2 or 3 times. That's what I always tell people. I mean, I'm not joking. I'm not like, you have to hear it 2 or 3 times. It's like eventually you hear it and you're like, oh, because I've heard these things about 1,000 times, probably from me just talking about them. But eventually you're just like, oh, that makes sense. That's what it's doing. That's what the leverage is. That's what this is. One of these times it just like, it clicks and you're like, oh, I can get it. I can explain it. So great job right there. So that's deleted student as residual, that's leverage, that's influence, that's how it all works together. And you don't want points to have undue influence. This literally goes back to the stat 201, QQ, straight enough, no outliers. So in 201, they always ask me things like, and it's cool, I appreciate it, because they're always like, how do you know if something is an outlier? How big of an outlier is it? And I'm like, well, we'd have to look at the influence. They're like, how do you look at influence? I'm like, well, you'd have to run an influence plot and get the high influence points. What makes things highly influential? Well, okay, that is the, that's going to be the leverage and the deleted student as residual. How do you get those? You just let the model compute it. So, but I love it. I love the questions because there's so many things to know. So what we could do, I think these are the functions. You can just run influence, and here's the influence of every point in the model. So if you wanted, you could literally compute the influence of every single point. I think it's Cook's D is leverage. I might have to look that up in the background. So I could sort these. I could find the highly. So here's the this is the weighted residuals with the influence, and I think Cook's D, Cook's distance. Yeah. So there's the leverage calculations on these points right here. So, and we should get a point. Let me sort these. Let's do, that'll do it because we'll put the high ones at the end. Yeah, look at this right here. Does everyone see this 0.24? This point right here, this point all the way up here. Oh, wait, is that 0.245? Is that point not there? How is this being calculated? Maybe we calculate slightly. Oh, wait, is this sorted? I'm wondering. Is Cookie's not? I'll look into that. What is it leverage? Maybe it's just leverage. It's just gonna be, oh, I thought Cook's D was leverage. Levels. Let me look up one thing in the background here. What are the points within the X inside? Oh, it just means that it's marked as a highly influential point. Anything in this quadrant or in this quadrant has both undue leverage, high leverage, and has both high deleted student as residual. And in this quadrant, they are marked as influential points. And in this quadrant, they're marked as influential points. And the size of the circle is the size of the influence. So you often see your biggest circles here. Like this one is almost going to be, but we just labeled it not. Let me get one thing right here. Cook's D. Oh, Cook C is influence. Okay, yeah. Dennis Cook made Cook C. So Cook C is influence. So calculate leverage in R. Is it Hats matrix? Is it Hats matrix? Look at that one thing real quick. I used to have to do all this stuff by hand. Hat. There we go. Let's get the hats values. Okay, 2 seconds. Let me look at I don't know why I'm so concerned with this. Okay, that's it. It's hats. If you look right here, we don't have to do all this stuff by hand. But if you look at this point right here, that point right there that you can barely see is 25.4933. If you look at this point right here, that's 0.03. Yeah, that's good. There's a 0. I was like, uh-oh. That's 0.023. And this point right here is yeah, this is correct. And then the influence size of the circles, and then the deleted studentized residuals. Was that being done by, yeah. We don't have to calculate this all by hand. It's all being done for us. We could always go and look at Petrie's code because Petrie made the influence plot. So if we go and remove this right here, you can see how he's computing each of the values. And you can see the code right here. I see Cook's distance and all this good stuff right here. And he should have hats in here somewhere. Hat values. There it is right there. And then there's the R studentized. So we could run R studentized on this. R student. There we go. And there's the R studentized values right there. That's the code that gets you all these values right here. But basically, R is computing for each one of these. That's something I really try to stress in 201 is that we don't do this stuff by hand. You don't have to run this. You don't have to solve each point anymore. That's what I love about using code. It's like, okay, we just found, 500-600, studentized residuals like that. We just have to know what a residual is. We don't have to calculate it by hand. We just have to know the concept behind it. And here's the concept behind the deleted studentized residual. Okay, let's do like a few more big topics. One thing I want to mention right here is Shiny. Now, I'm always trying to get people excited about coding. Here's one thing that who is not taking a course? You'll see how this applies. Who is not taking a course next summer session? Who is completely free next summer session? Who is completely free next summer session? Where did I put that? You wish. I'm so sorry. I feel so bad. Well, maybe oh, here it is. Found it. There you go. If you are completely free, it's 2 more classes starting. If you are completely free, you have Data Camp. And there's some really cool stuff you can do at Data Camp. So check this out. You ready? I don't think I destroyed this yesterday. We were going to add some stuff to it. Okay, we'll leave that in there. So this right here is something we have notes on. You can take a look at it. It's tree-based models. And all you do is you select the variables you want, and it does everything for you. All of this code that was ran in the background here, boop, you get your bar charts, you get your tree-based. If you remember decision trees from 201, yeah, totally, yeah. Yeah, Connor, start doing that. Start watching the videos and just get prepped and get ready. And Connor, you'll jump in and it'll be easy sailing. So Connor, great idea right there because you've got access to a lot of videos. Start doing that. I think that's a great way to prep. If you just got, just put them on in the background, just kind of I'm doing some work, clean the house, clean the apartment. Let me just put a video on and just hear what Brian says about this and see if it's making sense. Then you hear it another time, like Dennis was saying, and make more sense. So right here, oh, wait a minute. Ooh, we can do something with this. Okay, what is the misclassification rate of this model? What is the misclassification rate of this model? Who's got it? 1,000 points. What is the misclassification rate? Now, I didn't put something like this on the test, but you should be able to figure out the misclassification rate of this model. You should be able to figure out the misclassification rate of this model. Kind of. The rate, though. Brad, you're right for 1,000. You're right. But the rate, not the misclassification amount. That is correct for how many are misclassified. That is a correct answer for how many are misclassified. What is the misclassification rate? What is the misclassification rate? It's close to that. Is it that, Alex? I think Alex is right. I can't do the math in my head today. Let's find out. I feel like is it that? It is that, isn't it? No, is that? We'll find out. No, it was a little bit smaller. I think you rounded it. Yeah, there we go. I was like, it's close to that. I was like, I couldn't think. Yeah, because it's okay, that makes sense. Mathematically, I was trying to work in my head. I'm literally just every time I made that noise, I was like thinking in my head. Yeah, I was like, it's somewhere between 2 and 3 as I thought through it. I like right there, 1,000 points, Alex and Austin and Brad. So all they did was 4 divided by 150. And this is a 3-level classification, which is we haven't done in logistic. It'd be multinomial logistic. A decision tree can handle it really well. But this is multinomial logistic. We have not covered multinomial logistic, and I rarely work in that because oftentimes we're interested in a level of interest. The level of interest comes last, and in indicators, I am first. So we have those things that we should know right there. Levels of interest last, indicators, I am first. You guys are killing me, Brad and Alex. I'm glad I know you guys are all friends here. You guys want? We had so we had a random person join in on 474 after we went online. Some random person joined in, and they were kind of like making jokes towards people. And then I found out that they like someone in the class like emailed me and they're like, "Hey, that's we don't know who that is," and because the person like was cracking jokes. Um, oh, uh, so but then and I was like, okay, and we just blocked them on the channel. But I know I love you guys. Like you guys are, you guys make it so much fun. Like this is just chat room, fun time, enjoying. They're always, see, we shouldn't tell people to round. But look at this. You can change this and it'll recompute your tree down here. So when you think about the application of what we're doing, oh no, this has 6 misclassifications. So there are no friends here. What? Why are there no friends? Everyone knows F is for friends who do stuff together. That's what we always like to say. With this right here, this is Shiny. So if you're wondering why Brian mentioned using DataCamp, this is Shiny. And Shiny is a great way to learn how to do stuff. And look, it even does the formula for you. It does everything. You can just put it in right there and it redoes it for you. So when you think about, you can open in a browser. You could put this on the web. Yep, here we go. So you could literally upload this to your web page. It's all ready to go. You can just click it. You can increase font size. So you can be like, that's too small. And then it'll do it for you. So this can now be loaded to the web. There you go. You just made a web app for like, if you wanted someone to upload their data and run a decision tree, you could do this. They literally have these for regression. Like, I'll show you one. Let's go show a Shiny app for regression. Oh, yeah, is he? Oh, it totally looks like, I don't know the difference between the two. Shiny R regression app. You could literally, oh, this one's really new. A Shiny app for simple linear regression by hand. Did they? Okay, good. I think, okay, this person's uploaded it. Wow. Okay, cool. Oh my gosh. So you can add in the data right here. It's going to get mad because the vectors are different lengths. That should fix it. Should recompute. You can upload your own data. I have to look at this file. Oh my, and it's even doing Plotly. This is very new. This thing that this person created right here. Oh, I'm sorry about that, Alex. Sorry. Hope everything's going all right. Hope you're doing all right. But, like, no, we're rooting for you, man. You got it, man. Stay strong, Alex. You got it. If you look at this all right here, think about everything we've been doing in our class. This interpretation, make sure the assumptions. Oh my gosh. I need to find this and download it. You can download the report as an HTML. Oh my gosh. What is this? This is insanity. You can upload your file to this. Your data, CSV, Excel, copy your data, paste your data, copy the data, copy to clipboard. Oh, you can copy, this is CSV. So I think it's downloading the data we just put in. Okay, so it's downloading that data. Can you upload data? This is insanity. This guy right here, congratulations, dude. You made a really cool Shiny app. Search the page. Residual. Sure. No matches. Oh, it's like search your data frame. Okay, it's searching the data frame. Wow, that's cool. Who else thinks this is cool besides me? Anyone else? Access labels. Cool. You can call this height. If you can upload data, then this guy just, yeah. And now we've got the labeling of height and weight down here. I have no all the emojis. We're emoji only today. We're emoji only. Besides, I don't know where we can upload the data, and that's the only thing I don't like of this. Maybe not Amazon Web Services cool, but it's interesting. Yeah, exactly. And oh, that means yes. Or is it maybe not? Is it AWS, Amazon Web Services? But this is something you can create, and obviously he's got the knit. I have no idea. I think this is really cool. He's got the mean of the x's, the mean of the y, the number of observations, compute parameters by hand. No one's got time for that. So compute parameters in R, all this good stuff right here. What is this? What is this, Alex? Let me open a new tab. Oh, wait. Let me go over here. Oh, wait, what? I don't know. Well, here, 2 seconds, Alex. What does that meme, Alex? I don't know. I have no, when I see random, a meme. All right. Give me a second. 2 seconds. Be right back. All right. Okay. It's sharing meme time. Okay, so we should post that in the Discord, Alex, for everyone who wants to. Everyone wants to. We need a. You know what we need, Alex? Well, I don't know. We should. I don't know. No, we're not doing that. Oh man, it's always Alex is right though. It's always R versus Python. It's always R versus Python. So we always have the R versus the Python war going on. The war will never end, R versus Python. But here's the thing. Does anyone else in here code in Python at all? Does anyone else in here code in Python at all? Anyone ever looked at Python besides me? I should really get better at Python. I say that all the time, and I just don't have time to get better at Python. Python is very powerful. Python is very good. I'm sorry, R. No, like R a tiny bit. And so please take this to heart. One thing I'm trying to point out right here, and we'll get back more talking about like exam stuff because that's some fun today. I understand that trashes R all the time and talks about how great Python. Ooh, Brendan, you should be like, design something in R and be like, do this. No, it's so mean. Be like, you should design something in R, like make like an app like this or something. You can add in better visuals. You can be like, hey, look at this thing. I finally learned some Python. Like, it's point click. I made this interface right here. It's all this stuff. And you're like, oh, that's awesome. I told you Python's, but you're like, psych, this is in R. But if you look at a lot of the packages, here's the thing. And this is why, I'll do this. Plotly in Python. So one thing I want to point out right here is Plotly in Python. So here's Plotly in Python. And so these are all visualizations being made in Python. So this is Plotly, the thing that Brian loves so much. These are all visualizations, Plotly in Python. So Plotly, you'd be like, oh, but I really want to use Plotly. Plotly's in Python. Well, we'll just change what we Google right here instead of Plotly in Python to Plotly in R. So, and of course I've clicked this right here because I'm always doing stuff in R. Whoops, wrong button. Go to here, go to there, go there. So you can go to the same sorts of things for Plotly in R. These are just different graphics. These are line graphics. So all these graphics right here are being made in R now. And so when you look at this, here we'll look at a little Python code for a half second here. We'll talk nice about Python for a moment. So when you go over here, we'll look at some Python code making this. Cool. When you look at this right here, just think about what Brian was typing earlier today. Does everyone see here? We have this right here. I'm just seeing where that, okay, that's the end of the, okay, cool. This is the what argument of the dict function. Oh, well, they just kind of said it. That's the first argument. The first argument they're putting in there is their data. And then they're separating out the next argument, which is going to control the layout with the comma. And you saw me type something almost identical to this today. And it looks like this is, okay, that's the type of thing that, okay, this is actually not the first argument. This is the first argument right here. I got to watch my commas. They have it separated nice and neat. That's the second argument. This is the third argument. and cool. And data right here. And I'm seeing this syntax I don't know as well, but they're going inside of here and they're creating the data object, I believe. Someone tell me if I'm wrong with my Python stuff. And this right here is the values inside of here. You see 1, 2, there's 1, 3, 2, and you can see the 1, 3, 2 there, and then the 1, 2, 3 right here. And these are the values being used to make the bar. So you could change the bars and the values you want to observe, and the Y values are right here. The layout is the title, so a figure specified by Python dictionary, boom. So if you could take this, I think, you can put, it says in R, you can put a Python chunk. I'm gonna try something I never try. We're gonna go over here to an RMD, and we're gonna go down here. This is all the COVID stuff. And we're gonna go down here, we're gonna go to insert, Python chunk. I never do this. Okay. It might not have right libraries. Yeah, it's not. Python engine now requires reticulate the package if you don't wish to set the... I've never, yeah. It's like, I can't do this. That's a bummer. I was really excited. I wanted that Python chunk to work. So with this in mind right here, though, who feels like they kind of understand what this code is doing? On a scale of 1 to 10, 10 being like you completely understand this code, 1 being like I have no idea what this code does, who feels like they could understand this code a little bit? And maybe you could even take this code and make your own bar chart in Python by adjusting certain things in it. If you needed to make a bar chart that displayed a certain thing for you in Python, you could take this and do some edits to it and be like, okay, I've got my data. Let me load in my data here. A 7, yeah. And that's what you want to get at. The more you code, the easier it is. There's an entire Instagram page that just, yeah. And Alex is right here. Like R is really big. Yeah, it's like even I might be like an 8 or 9 because I'm like, okay, this is how they're making the data. This is how they're specifying the layout. These are the elements contained within the data, and this is the type. Like, so okay, they're calling this is like, and then this is what it is. It's type, and then this because this is what this calls this, and it's just interesting to me that those are characters. We can look at something more complicated because they always get really complicated at the end of these. Even when you look at how complicated this is, you just got the data points and you've just got the different things they're specifying. They're just saying the color argument equal to this. And this is the way in which they're doing the points and the names and the rows and the color. Yeah, it doesn't get too complicated. It's just like, what do each of these things mean? What do each do? And if you learn, I mean, you could look at this and mistake it for R code. Be like, oh, they're just putting a vector in of these numbers. Be like, wait a minute. But that's how they're specifying the elements in the vector, it looks like. So they use the square brackets for the elements contained within the Y vector, I believe. I don't code in this language. But once you get adjusted to it, it's just learning the nuance of each language. And there's just so many, like the box plots, just, oh, it's so beautiful. They're going to show that amazingly beautiful box plot and then not have an example that has that. Oh, there you go. Here we go right here. And one of the great things about Plotly is you can just literally deselect stuff and you could make whatever graphic you want to make from it. You could zoom in on it. And so you could just take and zoom in on a portion of this. You'd be like, let's look at just this box plot right here. And there you go. So that's what's super amazing about Plotly and all this good stuff. This is what I make in my box plot video too. What is that? Oh, is that a Raspberry Pi? What is that with Raspberry Pi? What is that? The Raspberry Pi. What? IM show. What is this? Scientific charts. This is why, like learning how to code. And so if I can instill one thing in you, we'll ask questions right now. We'll hop back to doing more questions. Wait. That's a Plotly object. Wow. What in the world? What is this? Read image arrays from image files. That's so cool. You can hover over and get like the value. I mean, that's crazy. Whoa. The things you can do with this, amazing. Raspberry Pi on Pi Zero, it's basically wow, that's awesome. I don't know what they're doing. Whoa. They have like yeah. It's absolute insanity what you can do with these. Like drag and draw annotations. What? Can you write? See, I don't even know. There's so many things that I go to these pages and I just filled area on maps. Oh, why are they not showing it? Once again, if I can instill one thing in you, it's curiosity, especially when you get to the 3D stuff you can do with these. You know, it's pretty awesome. Just like you can make 3D objects in Python or R. Like both Python and R can do all the Plotly stuff. This is actually the data set. If you look at this data set right here, this is the iris data set, which is what we were doing with R just a moment ago with this app. This is the exact same data set right here that we were looking at with the iris data set right here. And I don't know if there's a Plotly decision tree. Ask a question. Who's got a question about the test? Ask a question about the test. We're just having fun for our last 30 minutes today, talking about the cool things you can do. And Plotly decision trees in R. I do not know if these exist. I've never seen a Plotly decision tree. Decision tree using R part to produce visualizing decision tree in R. No, I still have not seen a Plotly decision tree. I don't even know how it would look. That's not a Plotly decision tree. Whoa. It's interesting, but no one's made a visualization I love. Who has questions? What is this? I'll take a look. I will click on it after class. Let me think. I'm over here, so I should be able to go to open a new tab. Oh, what is this? Total queries over 24 hours. So wait, what is this queries of right here? What is it queries of? Oh, is this your Pi? Is that your Pi 0? And like how it's working for you? That's really cool. That is really amazing. I love it. That's awesome. It's whenever you Austin asked right here, is the stuff on the response exam only going to cover topics after the midterm or anything? Only after the midterm. I didn't go way back in time. So it's only after the midterm covers from simple linear regression to everything we covered with logistic. And so it covers a lot of topics. And we will do stuff during the Kahoot today. We're just taking the last 20, 30 minutes right here just to enjoy some time together. And if I can tell you one thing to do, it's really to just practice coding. I know it sounds like it never ends. Learning never stops. So, oh no, Brad, I know, right? But Brad, did it get easier or harder? I feel like there's less time after the midterm. I think before the midterm, it's like we have to get you up to speed on coding. Like you think about what we did before the midterm is like the way we used to do this class, the Kahoot is at 3. At the start of this class, and keep asking questions. So keep asking questions right now and we'll keep focusing on that. Yeah. The thing about where we start you off with is we realize when you come into this class, you have no experience coding. Like, well, that's what we expect. We don't expect anyone to have any experience coding when they start this class. So we don't want to start people off with like, okay, it's day one, code this. And then people are like, I can't do this. And I do have to remember every semester. And I remembered at the start of this that it really is scary when you start 320. Like I bring you in the first day and I'm like, okay, here we go. We've got R, we've got it open. Let's just start coding things right here. And like here we can make a for loop and all these things right here. And we're just going to make a for loop. And it's like, people are like, wait, what are we doing? What's going on right here? What's going on with this for loop? What does it mean? And we should know right now, this will just print the numbers 1 through 9. I know quite a bit already about coefficients from econ class, but this was more detailed. I think after understanding the coding a little bit, the part was easy, but the mural got more confusing. Yeah, it's at the end, it gets pretty tough with especially multiple coefficients in models. And that's where we need to start focusing in on what does each code do? So let's do that right here real quick. Let's focus in on kind of the different codes we've learned and what's the point of them. So we're just gonna make a very simple model right here. You always wanna think about, can I make an example where I can understand the basics of it? And so the summary, what a summary does is a summary gives you the coefficients in a model. The summary gives you the coefficients in a model. We can see here, this is B0, this is B1. Then we have our standard errors, which are our uncertainties. Then we have the t-statistic, which is a standardized metric. And then we have the p-value telling us the statistical significance. Has been knowing when to compare models. Yeah, I'll do that next right here. Because the ways in which we compare the models is we need some sort of like metric we can compare them on. And the metrics we usually compare models on are the R-squareds, the R-squared adjusteds, or the residual standard errors. So we can make another model right here. We'll call this model 1 right now. So if we're going to compare models, we can make model 1, and we can make model 2. So when we make model 1, model 2, and model 2 only explains 2% of the variation, or 1.89. And when we adjust a more fairer measurement, hint, 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 when we make a more fair measurement, it only explains 1.75%. Now you'll notice that GPA is significant in explaining somebody's height, but what we can notice is if we make a third model here, which we put both of these in, we're probably going to see, oops, I overwrote model 1. We're probably going to see the variation go away. And model 3 not found. Yep. There we go. Now GPA, because of its overlap in variation with, well, it doesn't really, just doesn't add new information that's valuable to the model. So it wasn't due to multicollinearity. It just, in the multiple world, did not bring enough new information. So we can check right here if it's due to an overlap. It was not due to an overlap. It's just the variable itself does not have enough new information to be significant in the multiple world. By itself, GPA was significant, but that's only in the simple world. In the multiple world, it did not bring with it enough new information. There wasn't a big problem with the redundancy of information in it, though. Does that make sense, Brad? As I kind of went through and I added things to a model, and I went from a simple model to a 2-variable model, a multiple model, and we can see what's going on right here. We can add in, we haven't talked about this yet today either. Another big thing to talk about, we need a variable like handedness. So it'd be handedness. So now we have in the model somebody's handedness. And what do we need to do to look at the significance of handedness? Can anyone give 1,000 points answers right here? How do we look at the significance of handedness? How do we look at the significance of handedness? How do we observe the significance of handedness? The worse, yeah. Well, so the higher the VIF, the more overlap there is between the X's, and that's a bad thing. We do not want the X's, and we might remove it from the model. It just means there's more uncertainty, and James is right, 1,000 points, James right there, partial F, and Brad for the question, 1,000 points. Yeah, we want to run like a drop 1 right here to take a look at, because this is a 3 plus level, excuse me. 3 or more levels, we have to run a drop 1 on this, which will remove out handedness from the model. And we can look at the significance. And I did forget. I always forget. There we go. So now we're looking at the significance of handedness in this model. And handedness is not significant. It drops out everything with handedness in it. So it's going to drop out from the model both handedness right and handedness left from the model. And look at a model with handedness left right in it and model without it. And with the variable removed from the model, it does not bring with it new information. So handedness as a whole, both variables being removed out of the model, does not bring with it new information. And everything right there, this is a partial F, it is an effects test, and it's done via the drop 1 function inside of R. So knowing that right there, like why do we use the partial F test is very important. And trying to think what else. Confidence intervals, we can do confidence intervals for coefficients of the model. So confident. There we go, confident. And we should get confidence intervals. There we go. So these are 95% confidence intervals for the coefficients of the variables in the model. And what you'll notice is the coefficients here contain what value? The coefficients for the confidence intervals contain 0, and that goes along with us seeing that, and we'll show it in the output. Here's this, and here's this. It'll give you the so let me go to Brad's question right here. Drop one always gives you a partial F, which is an effects test. The reason we change it to chi-squared is if we have a categorical variable. So if we have, the reason we change it is if we have gender here, and now we need to add binomial, could think for a moment. So now, right now, we need to go, should be model 4. Now we need to take and do the drop one, and we need to change the argument to chi-square. And M4 not found because I didn't make it. Yeah, chi-squared is for categorical. Yep. Handedness was almost significant in this model. So we have to change it to the chi-square when we do this right here. So chi-square is for categorical, and the F is for quantitative. Yep. And so these are both drop ones still. The drop one's always a partial F test that runs an effects test by removing one variable out of the model. And when we put the chi-squared on here, it's just for the categorical variable. Yeah, categorical Y. Bingo, bingo, bingo. That is huge right there. Because this is a categorical X, but that doesn't matter. We're predicting a quantitative. This is a quantitative Y. So this is quant Y. And this is categorical Y down here. So this is cat Y. So very important we know which type of variable we're predicting, because this is logistic regression and this is regular old vanilla regular old regression. So big change right here when we go from the LM to the GLM. The GLM is the generalized linear model. And once again, we saw some tricks about how we could still use GLM, but we use mainly GLM. Give us something. I've probably said about 50% of the exam today. Like, this has been a huge, I mean, stuff on the screen right now is on the exam. Drop one's definitely on there. That's something big right there. If you were like shaking your head and following along with everything today, so lots of Python. Like how to affect trends of models gives 52%. Okay, what's another thing that's on the exam? Trying to think of something I haven't said today that's on the exam. I've given away so many things. We talked about interpretations. Interpretations definitely on there. We talked about misclassifications of matrix. That's definitely on there. The naive model, which is why I brought up, why we went on this tangent about this right here. See, the naive model, it's hard to say for this what the naive model, it's because it's a 2-level classification. That's why I didn't mention, oof, I don't want to be calculating those crazy numbers. This one's kind of weird for a 2-level classification. Okay, let me do our model right here we created, and let me do the classification of this. So we should be able to do confusion matrix. And is it the red class one? I think it's the red class one. I think I'll do it. Cool. Go ahead. Calculate with these numbers right here. Let's zoom in on it. Let's take a snapshot of this. Let's try to calculate the misclassification rate, and let's calculate the misclassification rate of the naive. So let's calculate the misclassification rate of this, and let's calculate the misclassification rate of the naive. So what is the misclassification rate? What is the misclassification rate of the naive? What is the misclassification rate? What is the misclassification rate of the naive? Any guesses? Who can tell me either one of those, the misclassification rate or accuracy is the complement of misclassification. So no rounding. I love that right there. What is the misclassification rate? Something above my head. Oh, that's that. It might be. Is that of the model or the naive, Brad? Is that of the, that looks to be of the model, right? That looks to be of the model. I'm guessing that Brad looks to have it correct. That does look accurate. Great job, Brad, right there. This and that. I'm going to circle something else right here. And this right here is the accuracy, I think. There we go. So, yep. And here, let me try this again. Okay, cool. That actually worked. Cool. Okay. So the green is the accuracy of the model. The red is the misclassification rate of the model. So the misclassification rate of the model is going to be this right here. No rounding. Brad got right there. And the misclassification, the accuracy of the model would be, you can just do the complement of this. That's the accuracy of the model. So the accuracy of the model is the percent of time it's right. The misclassification is the percent of time it's wrong. Oh no, you're fine. That's close enough right there. And so now, if you want to do of the naive model This is where people get stuck. And Grant, that might be right. Grant, 1,000 points. I think Grant might be right for the naive model. Grant might have the accuracy of the naive model. Let's find out. Is Grant correct on the accuracy of the naive model? Yep, that's actually the naive model. Great job. So would the total number of misclassification in the model be... Oh, no, that's the total number of observations. That's the total number of observations. So good question right there. Does that make sense, Henry? That's the total number of observations. There were 699 observations. And then this kind of goes back to doing categorical data, because these right here are the marginal displays. So within this, you have people who are predicted a certain thing and are a certain thing, and then you have the marginal displays. So the naive model would be the total for whatever reason is the majority total observation. Yep, when you look at the naive model, you only look at this. This is when you look at the naive model. Now, what is the naive model going to predict for everybody? What is the naive model going to predict for everybody? What will the naive model only look at that? So here's a hint. While people are trying to figure out what the naive model will predict for everybody, what will the naive model predict for everybody? And basically, go into greater detail, Brad. You are correct. You are correct. What will the naive model predict for everybody? So it's real get confused because it says predict right there, but you don't focus in on that. This is the naive model. Female smokers? Nope. Who's smoking on here? Just female, right? Just females. There we go. It's going one step further. So it's just going to predict female for everybody. So, or whatever we are viewing as the other no, there's only one category. We're just predicting whether or not someone is male or female. We're just predicting their gender. Does that make sense? So the predicted is whether we predicted male or female. The actual is what they actually are. And the naive model only knows what people actually are. So we're just predicting, if you look at the R part of this, we are just predicting somebody's gender right here. So the X's have nothing to do with it. It's just going to be the Y variable, which we're predicting, and we're predicting gender. And we know that most people are female, so we will predict everybody is female. So how many will the naive, this is a step question, how many people will the naive model get correct? How many individuals does the naive model get correct? How many individuals does the naive model get correct? How many individuals does the naive model get correct? 386, exactly. So it'd get right 386 divided by 699, and that's the accuracy, and that's the misclassification rate. So the accuracy of the model is the 55% female, the misclassification rate is the 45%. And you could figure this out really quickly with the R code. If you just go over here and you do something like table, and you do survey gender divided by number of rows in gender, and that'll give us right here. Oh no, what did I do? Oh, ha ha ha. There we go. And yeah, this does it right here. This gives the same value we observed just a moment ago. With this right here, if we do, there we go, 55.222. And so we can get the values with the confusion matrix. We can get it with the code. Lots of different ways to get this, but it's just the percent female in the survey. And since 55.22% were female, we would predict everybody is female. We just predict the majority level because it's the most common level. So we're going to predict the most common level to be the level that everyone is. It's just like, okay, most people are this, everybody is this. So we've dropped a lot of hints today. Any other additional questions? We have the Kahoot at 3. Yeah, let's get it. You got it. Can you see it right there, Brad, really well? Or let's go back to the Word document. I think I still have it in the paste. No, I've got that in the paste. Let's see. Here, we'll make it really big. And there we go right there. That is the confusion matrix. What questions do you have about it? What are you wondering about the confusion matrix? I've got some really cool codes, and there's so many cool codes. But if you are here, if you've been watching, definitely look into coding. That's like Brian's advice for the rest of the summer. I know it's a busy summer. I know the world's all crazy right now. But with the Data Camp subscription, if you start learning more about coding with maybe SQL, with Python, with R, if you practice up your skills, it can only help you. It can only get you more abilities and more technical skills. And sometimes you have to look at that. I like that, Dennis, right there. You're right. Dennis, you are exactly right. Oh, the total number of misclassifications? Is it for the model? So if you want to do the total number of misclassifications, this is the total amount that have been misclassified. So we'd add together those two numbers because these people were predicted female, they were actually male. These people were predicted male and actually female. Does that make sense, Henry? So these people were misclassified. You have to look within the predicted and the actual, and this is for the model. So this is for the model. The naive does not know any of this. The naive does not know these predictions. So, yep, and so that's for the model. And then if you look at the naive's misclassification, the naive does not know those predictions from the model. The naive only knows what things actually are. So now the naive only knows this info. You're welcome, Henry. Great question. That's just, I like when people are like, this doesn't make sense. Can you explain it? And that's what we do. So the naive would know most people are female. It's going to predict every single person is female. So the naive says, okay, most people are female. Everybody's female. Gets those people right. And then it would get these people wrong. Those people would be, the people I've circled right there would be predicted to be female. Since most people are female, everybody gets predicted female. The naive just predicts the majority level for everybody based on the distribution of the Y. And so I was doing this with the R code just a moment ago. I was just finding the distribution of the people who are female, and the naive model would just use that. It would say, well, most people are female, or, you know, most people could be male in this model, but whatever the majority is, it just predicts the majority because that's the, I mean, if most people are this, you're going to get most right with this. So it just does it there. It's just tries to err on the side of most are this, then we predict everything is this. And it gets into some interesting like false positive, false negative stuff. Like what is the cost of a false positive, false negative? We talk about that a little bit more in 474 because that's a cost benefit analysis then. What other questions are there? We just got a few more minutes. Really good stuff here at the end. We covered a lot today. What is everyone thinking? Did everyone have a good summer? Did you guys enjoy the class? I hope you did. I hope it was a good bit of fun. I hope it was a nice 8 a.m. wake up. Hope it wasn't too random. Monster Cat's not. I got my rainbow button and everything. We never hit the rainbow button anymore. Oh no, Monster Cat is coming. No. We can't have them appear. The computer's a little stuttery this morning, Dennis. Maybe it's because I left it on last night. I don't know. This computer should be able to handle being on for a day. I want to look at the resources between class and see what it's doing. Monster Cat has joined the chat. No! Sounds like Smash Bros to me, like Monster Cat has joined. I hope it wasn't like my teaching was a giant puzzle, but the class itself, like the coding and stuff was a giant puzzle. Not that like being successful. Nice, Alex. Alex, I hope you're doing well. I hope, yeah. It's, you know, the numbers are pretty interesting as of late. You know what's weird? There has to be a misreport. This is why I'll tell you. If there was, and this is why I'm just like, what's going on with the data? What's going on? Because I know this can't be correct. This can't be. Oof. Okay, so this is Tennessee's COVID numbers. And there's no way. Does anyone see a point on this data set that they're just like, no way? Does anyone see a point, and I'll hover over it for you in a moment, but does anyone see a point on this data set where like, I don't know about that. What happened? What's going on? They need to fix this. They didn't. Okay, so what happened here? Did they just decide not to report? So what's going on with that? Like what is, do you know something about that, Alex? There was an error? Well, yeah, apparently. Yeah. Because I don't think that's real. Because that's so much of an outlier. Exactly. And yeah, and I'm like, what's going on? Oh, really? Yeah, I don't know what's going on. That's just variation within the data. There's a 7-day lag trend on this. I want to show. Are we just not getting? Oh, did they send out the news on this, Alex? Here, let's see. Alex got her here. So this is, yeah, it says like, did say like something happened to their, do extremely high volume. There was in recent incoming backlogs, the queue approximately shut down. Yeah, yeah. So what are they going to do? What is, Lacey, that's not, um, Keaton, you're cracking me up right there. Good to see you, Keaton. Cracking me up right there. Um, so that's interesting. And also we had 2,000 cases there. So the reason it spikes up and down, there is there's a cyclical pattern to this. Like you can always tell. When is this? This was that was Monday, right? Monday's numbers are always low. Maybe it's because like we're reporting like weekend numbers. Um, Man, I'm so sorry, Alex. Alex, I'll stop talking about this. I'm sorry. Let me not talk about this anymore. I'm sorry. Alex, we're rooting for you, man. I don't want this to be too stressful. Thank you for volunteering. Thank you for helping out. Thank you for being there because this is really tough times. And, like, thank you for it looks like you're taking the proper precautions. Um, but no, we're there for you, man. We're there for you. You got this. And, stay strong, man. Oh, so that's why Tuesday numbers. Yeah, I should look into more because you get this cyclical pattern. Like, you have to realize that there's a lag right here, and a lot of sites will plot like the 7-day trend. And the 7-day trend has been, if you were to plot a trend line through this, you have to do a moving average. Yeah, and the biggest thing is, like, I'm obviously worried about this stuff. The biggest thing, class is over. Yay! um, there's the most vulnerable people. Like we should obviously be worried about it because we don't want to pass it along. Like I'm in a little higher risk group than everyone in the class. Every guy I've seen has just straight upward trends with a very occasional dip. Yeah, this is the daily right here. But if you plot through this, you get kind of a smooth. And what scared me is I noticed that the derivative was changing. If you're like, I'll show you what I'm talking about. When you do graphs and stuff, you have to look at the derivative of what's going on. And so what's important is if you look at like a moving average on this graphic, what we want to look at on this graphic is the following. We want to think about the derivative. It's calculus. So if you're here and you like calculus, this is the thing. So if we're going to plot an average through this, it's going to smooth through it, and it's going to go like this. So, I don't know. Actually, I literally look at this every day. Okay, I think the derivative might be changing. I've got a little bit of hope. What started to get me was about here. Was it there? I was somewhere in here. Somewhere in this range right here, I was like, we are not, like, the derivative, we want it to be going down. And it was flattening out. And so when you look at this right here, you can think, okay, we're going through this upward trend, we're going through this downward trend, and then we've got this trend right here where it flattened out, and then we've got a change right here. And especially there's an increase right there. Like derivative is rate of change and everything. So you can look at, second derivative and first derivative. But right now, taking the derivative would change the number of infection points. So does that change? Well, it would. So does everyone understand, like, this is calculus and stuff, like first derivative and second derivative? Like, hopefully I'm saying these things correctly because I don't do as much calculus. But the first derivative is going to show you, I believe, the positive or upward trend of it. And the second would be the rate of change of it. So if you think about the first derivative right here, you're going to see a change right here. So it's going to be like I don't know. It's interesting to put in context what things mean in calculus, because are things increasing or decreasing, and are they increasing at an increasing rate? I think that's second derivative. Please correct me, calculus people, if I'm wrong. But like when we talk about, is it increasing and is it increasing at an increasing rate? So we want to focus on things like the first and second derivative of this. And so looking at the time periods, I started to get worried in this time period, especially when I started to see the change within here. And you can think about what happened right there. Like around June 1st and stuff. Like, I don't know, this stuff is not political. It's epidemiology. Yeah, that's kind of what I'm getting at. Um, and that's where we're seeing a lot of the infections right now. Is a lot of the early reopens. We're seeing a lot. I mean, it's just facts. We're seeing a lot in Florida, Georgia, Texas. I don't want to miss state to state. California. Well, if you do the per capita, that's the thing you have to look at too. Is you have to look at per capita infections. So when you look at the per capita infections, the population of, so I'm gonna say a wrong number. I mean, I look at these numbers and then I double check and be like, okay, what's the per capita? Because if you, what you want to do is you want to go to a state like Florida, and you look at Florida, and oof, you see you can't extrapolate the trend yet on this because this is enough to get an idea of the trend right here. Like it was flat in Florida, and then we see this upward trend. Yeah, it's not political. This is not political. This is nothing I say is meant to be political, and I'm no one take anything I say political at all. It's just epidemiology. It's just staying safe. That's all it is. And I'm not an epidemiologist. I'm someone who looks at the numbers, which I do have the numbers. This is one of my students. Where's his? Here's the, yeah, here's the file rate. And oof, it was, I swear. So he's using Plotly and all this good stuff. This works on my Mac. So is it going to work today? What? I don't know. What it? Which one? What is this right here? What is that, Alex? um. Oh, it's a cool website from Chattanooga. Let me do this right here. Hard this screen. Yeah, I never want people to think anything I'm saying is. Oh wait, cool. Oh, okay, cool. Oh, nice. Yeah. Is it this like within their county? You see, look, here's the smoothing line. That's exactly what you need to do. That looks like a 3-day smoothing average. A 7-day smoothing average is going to be a lot smoother. Does that say if it's a smooth? What's smoothing? A 7-day average? Okay, shocks me that's a 7-day and it jumps that much. The higher the moving average, with these smoothing averages, the smoother the line will get. So I thought it was a 3-day because 3 days will jump more. I mean, like the single day will jump a bunch because it's singular data, individual points. And you see, this might all be Plotly. It's a very similar thing that they're doing. That you see, there's this right here is a very, which is kind of good. It's kind of random. It's hard to, I mean, you would just say the mean right now. We had this, yeah, it's very hard. Here's active cases. They're reporting it looks like weekly, not on the weekends. Was that? I'm wondering why that Friday was off and why there's a 3-day gap, and those are probably weekends. So you just want to look at the structure of the data. So the active cases are slightly increasing, but once again, let's take a and look at this well, that's very interesting. And that's all the way to June. And yeah, they're doing the moving average. That's good. You want things here like a moving average. Yeah, it's just stats. That's all it is. Hospitalizations. We get the ICUs. Okay, so we're seeing a rise in ICUs. PUIs? Non-ICUs? What is PUIs? I don't know what PUIs is. I know ICUs in intensive care unit. And yeah, so we're seeing a rise in the ICUs, but it's stabilized. The ICU numbers look to have leveled off. And so you don't want to say they've gone down. It looks to be like a lot of process control can be done with this too. This is really cool. Oh, wait, what is this? Hospital beds available. Of course. Well, if you're seeing a rise in ICU, you're going to see a decrease in hospital available beds. I mean, that's obvious. Testing. So here we go. And is this the percent positive? Cool. Okay. So, yeah, that goes to, is more testing showing the more positive, but I think still you have to do this. Like, here's the thing. It's a moot point whether or not testing, like that's totally moot. It just doesn't matter. What matters is we do testing because we have to identify, and then we need, patients under investigation. Cool. Thank you, Dennis, right there. We have to do testing to identify and to help people quarantine, because if you don't do testing, it's a problem that feeds into itself. By not doing testing, you need more testing. So it's like you have it regardless of whether you test. So if you don't test people, they don't know they have it, and they're going to spread it more. So it's just a moot point on whether or not, I mean, you have to test. You have to have the testing available. You have to have people who have symptoms getting tested. That's the way you fix the solution. Andrew with suggestions in the chat. Is this Plotly? Oh, this kind of looks like Plotly a little bit. It's kind of like a Plotly type thing. Cases by age range. Is it cool? Sets the. Oh my gosh. That's my age range. 3 weeks, it'll be done. Oh, hope. Do we have data? We want the data to support that. We want all the data. There's a cool site on it, though. It's a really cool site. And I think the best thing we can do is, one, stay positive, two, encourage each other. If you look at the psychology of this, encouraging COVID Act Now, cool. What is that? China try to. What did they try to do? Brian, I've been trying to open the take home for 45 minutes, even after I saved and deleted the. Send me that, Ben. Send me it. Did it open before, or is it just not opening now? Send me. Did you get it open, or is it not just opening at all? And it shouldn't be a TXT file. Try a different web browser, because if it's downloading as a TXT, you should be getting an RMD or an RDART data. Send me some stuff on that, Ben. Send me, like, Brian, it will not open, and we will get it fixed up as soon as possible. Did it open before, though? Did it open before? It's cool sites. I like it. What is? Awesome, Brad. You're welcome. Thank you so much. Thank you so much. So, Ben, send me that file. Send me a screenshot of what's happening, and we'll try to figure it out. But you can just see the graphs. The graphs are awesome. So, pretty crazy. All right, let's see. We'll hop out of this right here. All the numbers. All the numbers. Once again, it's all data. I don't know why this works on my Mac, but not on my PC, which really bums me out because I want to. We can plot all this out right here and look at the different cases for like March, April, May, and June because it's all just data. And this works on my Mac, and I have no idea what's not working on the PC. 1 billion. We'll find out. We'll find out very shortly here, Andrew. We will be right back. See everyone soon. Bye. Hey everybody, it is a random day, just random. Let's do this. Can't play for too long. Monster Cat's gonna hear it in the video. Be like, used it 3 times in this video. We're finding out how long exactly we can use that before Monster Cat takes the video down. How is everyone doing today? How is everybody doing? I know Monster Cat's gonna. Sorry, Monster Cat. Sorry, Monster Cat. I want to know why this works on my other computer, not this one. What's up, Ahmed? Good to see you, Anisha. Good to see you, Ahmed. Good to see you, Andrew. Stressed? Oh no. What about, and I am considering this, because the biggest thing, I look at emails between classes. What's up, Jacob? Hey, Carly. Hey, Sarah. How about if we make the take-home due, oy, I will do it. I'll make it due tomorrow. I'm just thinking of my plans. That Oy was like, okay, then Friday I'm doing this, and Saturday I'm doing this, and Sunday I'm traveling to Texas. Let's make the take-home due tomorrow. You can still do it tonight if you want, but we'll make it due tomorrow, and I'm going to tell 320 that also. I'll send an announcement to them. So, and then Friday I'll be like grading it and stuff, so I can get grades done on Friday. Does that work for everybody? Because I've gotten a few emails. I only do, one thing I always want everyone to know is, so, sorry, people emailed me and asked stuff. You're welcome. Okay, so we will do that. I'll tell 320 also. I consider these things. You're welcome, guys. You're welcome. You're welcome. Yeah, so, and I know you guys are working so hard. I always just listen to the students. That's the best I can do, is listen, take in what everyone has to say, update, not stressed. Turn in both. Yep, the Word document and the RMD. Oh, you guys are so, look at all those hearts. You're making me smile. I mean this. I know everyone. I'll tell 320 also. So I'll say 474 convinced me. I say you say thank you to 474. We're working together. We're a team. So hopefully no one's like, Brian, I just spent the last day or two working on this and you ruined my life. And if I had known this, I wouldn't have done this. I update things as it goes. Like I understand. Like I try to. Dennis, that's awesome, Dennis. I want to, do you know, I'm hoping he, okay, guys, tell me how hype this would be. A former football player from the NFL who played for UT, I messaged him yesterday after he told me, because I've got a stat tool on Twitter, which I never use. I made it in like 2016. And so I had to find the password for it, because I hopped on his Twitch because I saw he was on Twitch, and I know he does streaming and stuff. And so I said on Twitch, I was like, hey, I teach at UT. Would you be interested at the start of the semester coming in and just saying hey to students and maybe hyping them up? And he's like, yeah, sure, hit me up in the DMs. Yeah, hit me up. I'll talk to you about that. And I was super hyped. So possibly we might have and like we're so lucky because we've had Julio come in. I want to get Julio back on here. Julio said, hey Brian, we need to catch up, but I really like the support we get. And don't worry, if this doesn't happen, it's totally cool because it's his time. He's living his own life. He's doing his own thing. But I always think it's cool when we can get someone on here. We got the sports on today to appreciate that. So it's always cool when we can get someone on here. What would you think of that? Would you guys reappear if you saw on a Stat21 stream, like and I'll like send out an announcement, we could put out the word, we can put it through the Discord, like so-and-so will be here. I know, I think it'd be super cool. Was he an aerospace engineer? It's Arian Foster. You would reappear? Yeah. I want to do it at the start. If we could, I'd want to do it at the start of the semester when do what? Oh, Josh Dobbs. Oh yeah, if Josh Dobbs want to do it. I mean, who'd ever want to do it? I want to get people hyped up for like what we do. I want people to be excited, and just having like former Vols come on and give some encouragement to students is really cool. They don't have to. I mean, once again, everyone's got their own life, everyone's doing their own thing, but I just think it's fun. I think it's fun to like, oh, so and so is here, just to like get people hyped. Like I really want to make maybe some like if they would be interested, I'd want to make like, because I want to get Julio to do this too, and we just haven't had time. And he said he'd totally do it. Julio is just, shout outs to Julio. Like, not saying anything about anyone else, but Julio has been so supportive of like the Vol community. He comes back and like helps out with the baseball team. He's been such a huge supporter. Like man, he's such a nice guy. Like Julio, thank you, Julio. So that's a huge shout out to Julio. And no one's required to do anything like with doing all these things, but um, played him in Madden. Wait, what? Just hype me up and say so. But we'll see what happens. We'll stay. I'll keep everyone updated. Um, I don't know. And once again, then you see, we could get like Peyton on here. Could you imagine if like right now in the bottom corner of the screen, Peyton appeared? Peyton Manning was like, "Hey guys, good luck on your test." See, that's what, and like Arian saying something like that, getting Arian just to be like, "Hey, Stat Tool One, good luck on your upcoming test. You guys got this." Is like being like, "Hey, this is Arian Foster. Good luck on your upcoming test. You guys got this." We're rooting for you, Stat Nation. So just getting any of them if they'd be interested to kind of give a shout out, and we could play that then before a test or something. So that's one of my goals for the channel. Oh, he was? That's awesome. Yeah, like that's so crazy. It's kind of cool, like just to give like some props to him. He's definitely his insight, and he's very like focused on science and learning, and so that's one of the, I think I hold a lot of value in his like value of education. I think he sees a lot of value in education. That's kind of one of the reasons I kind of reached out to him, is because to me he kind of embodies that idea of we should all be learning. So we'll talk more about our learning in a second here, but I think he holds a lot of really good kind of like, we should be learning, we should be investigating things, we should be looking into things. And I know he really values science. So I'm like, that's awesome. And just giving some encouragement. I have no connections there. So yeah. Okay, so that's got that. That's got that right here. We got the sports on today. This is all I know of sports. But with this right here, I mean, yeah, if you guys got connections, and she was like, sure, I'll be like, hey, Stats One, good luck on your test. Sure, if any of them want to give shout out videos, if one of them wants to say like, hey, do a great job on your test, we're rooting for you, just to give you guys something really awesome to get excited. And one of the great things is, we don't want to bug them. Like I was like, oh, I'm just gonna ask him. I'm gonna see. Yeah, and that's the thing too. Let me just say that real quick with Dennis. Dennis points out with sports stats, because we're talking right now too, more about getting UT involved with sports analytics. And one, did everyone see that announcement I sent? Who saw the announcement I sent out about working with the football team? It says it's not paid at first, but could you imagine somebody being told, good, awesome right there. That is awesome. Now, I know one person at least told me they did, so I'm so glad to hear you did, Andrew. Could you imagine someone being told you can work with recording? Wow, Andrew, congrats, man. Congrats. Could you imagine someone being told in Knoxville or somewhere in Tennessee? It didn't seem like, I don't know. And then that's the thing. Try to like bring some analytics in, bring that, like I'm going to make data-driven decisions. And like the more you can kind of, like charts, graphics, figures, data-driven decisions, here's how I'm making this, like showing them. Sometimes you just have to figure out a way. So Vadran, good advice right there. The more we try to go by the data, the better decisions we can make, I think, personally. Because you look at like, did I say Moneyball in the email? I was like, oh, we can Moneyball UT Analytics or something like that, UT Sports Analytics. I might have made that joke, or like, oh, I'm such an old person now. But we try to think of data-driven decisions here. And so if you're doing recruiting, you want to base it on the data. So, I'd be asking them, what data do we have? How would we be doing this? And, where do we see the most successes in recruiting? And I know a lot of people are, hopefully they have some data on it. Like, what data have we collected? What do we understand about our recruiting process? Because it's really how much room for improvement there is in sports where there are just hidden correlations. Yeah, exactly. Dennis points it out completely, because understanding the process of a sport, like we're literally hopping into topics right now. It's because what we have is like lurking variables. We have these variables that are the true sources of variation, but maybe people have gone by like this gut feeling by a long time. They've just been like, oh, I feel like it's this way. But then if you analyze the data, you might see like, okay, it's actually this other variable. So 320 review question, 1,000 points right here. How do you figure out what variables are actually the variables that are actually the ones coming into play in a model? How do you figure out you need to learn football already? Oh, that's too crazy, Andrew. how do you figure out what variables are actually the sources of variation? So Dennis might be able to help us out. And here's the answer right here. I'm going to start talking about some 474 right here. How do you figure out what variables are the actual sources of variation? How do you figure out what variables are the actual sources of variation in a model? How would you figure that out? How would you make a model? And we're kind of doing it right here. The answer's right there. That's the answer. That little dot is the answer to figure out what variables are the actual sources of variation among all your variables. You do what with them? It's so funny. That's a concept right there. That dot in and of itself is a concept in multiple analysis when you analyze multiple variables. And that's the answer. The Wildcat formation where the running back has the ball snapped to them was formed after a coach looked at the data from previous games. Yeah. And Jordan's right too. Jordan and Dennis, you're totally right. You put them all in the model. You put them all in and you let them all kind of fight it out right there. So that dot right there means you put all the variables in the model. So that's why we're doing that. We're putting in every variable and then we're seeing what variables kind of win out. It's like, okay, let's see which of these really does a good job. Well, they have to work against each other now. Not like in a bad way, but they're all vying for who's the winner that explains the most variation. So when you make this right here, and don't worry, that's just we get some coefficients that are 0. I think we can look at it. I rarely look at these, but I think we can look at the coefficients in here. There's the coefficient names. So that's the names of the coefficients in the model. And we should be able to model info. Here's the model info. Oof, we don't want to look at that. That's way too much. Man, there's so much that is done with the train function. Model type, method, results. Here's the results right there. We mainly just look at the output because it's more predictive modeling. 474. What is this right here? We just asked 320 of this. What is the RMSE? You should know what RMSE is. What is the RMSE? 100,000 points. We're going to divide up by all the people who get it right and give info on what RMSE is. What is the RMSE? I need as many right answers about what RMSE is. Typical miss. Boom. Root mean square. Correct. Average miss. Correct. All these are correct. Typical miss. We're going to give I think we're giving 10,000 points to everybody because we're dividing it up. It is root mean square. That is literally what it stands for. It is typical miss the model makes when it makes predictions. One thing we talked about in 320 is why do we not use just mean? Why don't we just use mean error? So why do we not just use mean error? Why not just use mean error? Like this is the mean error if we just were to take and average together all those red lines. Why don't we just do the mean error? Why not just do mean error? Any ideas? Why don't we just do mean error? I mean, we do the root mean squared error, but why not just do mean error? Like what would be mathematically wrong about that? The negatives and positives are included. And since there's some negative, some positive, what would the mean error always be? What would the mean error always be? If we did mean error of these, it'd be 0. Mean would be 0. Because if you just did the average error, the model works in a way that it reduces this. And we want to look at the sums of the squared error or the root mean squared error. The reason you don't report the sums of the squared error is because it's in squared units. So think about this. The sums of the squared error. Well, that's just the total amount of error. Well, why don't we take the sums of the squared error and take the average of it, which that's literally what a mean is. It's the average of all the observations. And then you take the root of it. So sums of squared error can be turned into, so the sums of squared error is basically turned into the root mean squared error. So when you think about what sums of squared error are, and you think about what root mean squared error is, they're very similar. They're very, very similar metrics. And the reason we use the root mean squared error because it's in units of the problem. So the root mean square error is used because it's in units. And here's one thing you have to instantaneously know. The root mean squared error is for what types of y? You have to instantaneously know this. You have to know it like that. Root mean square error is for what kind of y? Like, boom, you have to know it. What is root mean square error for? What kind of y? Quantitative, boom, right there, got it. Root mean square error is for quantitative y's, numeric, quantitative, all that good stuff. We can't get it for categorical. If we switch over to categorical, what are we going to use? And the train data. Let me look at the train data we're using right now. If we switch over to categorical, what are we going to use? Actually, I'm going to use a better function. I'm going to use some good stuff right here. What are we going to use? AUC, Inisha. Great job. 1,000 points Inisha right there. You are right. We're going to use AUC. Glimpse allows you to take a glimpse at it. And we got day pay plan. Yeah, I should have realized pay plan was in here. So P minus capital P. Now watch this. This should create. It should get mad at me. Is it gonna get mad at me? Yeah, there's 11 warnings. Good. That's what I wanted because I'm wondering what it'll do. I just wanted to see. Oh, come on, computer, don't be weird today. Oh, it actually switched to accuracy. Oh, because yeah, it will do that by default, but it's not going to do AUC by default. So accuracy or AUC are used right here, but we have to set up a different fit control. And okay, let's see if Brian remembers everything we need in the fit control. So we need fit control right here. We're going to store into the fit control, and we're going to use the function tr control, train control, and in the train control, we need the following. We need the method. Hey, there it is right there. We're going to do method. You could do boot if you want, but we're going to do CV. You could do repeated CV if you want, but there we go. Number is going to be 5. And then here's we get to the problem part. Okay. So the two things we want are to class summary, and this equals true, right? And then what is the other one? It's summary function. No, wait, to class summary equals, and then what is the last one on here? See, I'm going to cheat. To class summary. There it is. Summary function. Class probs equals true. There it is. Class probs equals true. Class probs. There it is. It's so easy to make a mistake on those. And so the more you practice typing them. There we go. Just, I know it's the two things. I know this is going to fit for AUC right now. Summary function equals to class summary. This right here, you do want the class probs in here. We are missing a comma. There we go. Now it'll like it. And now it's going to fit on AUC. So now we get ROC AUC, and we should know that ROC is the percent of the time the yes class gets a higher probability than the no class. So we properly order the yes class with a higher probability than the no class 72.25% of the time. So the ROC right here is pretty decent. You know what we can do though? We can go, and we could do this with the decision tree. We've got everything set up right here just to change over to pay plan, and this should work. We've got the CP grid, and let's take a look at this. Everything should work. Yep. And then there's the results. Oof, oof. That's not good. That's not good. Let's talk about why. Why is this not good? That's interesting. The decision tree did so much worse. If you look at this right here, do you want higher or lower ROC? Do you want higher or lower ROC? Or AUC? And it's probably better called AUC. ROC is the curve. AUC is the area under the curve. You want higher AUC. Yep. You want higher accuracy. You want higher AUC. Do you want higher or lower RMSE? Do you want higher or lower RMSE? With RMSE, do you want higher or lower? Would be two models. If you compare them, higher or lower RMSE is good. Lower RMSE. Lower because it's typical miss. You don't want your model to make misses. So you want the typical miss to be small. You want the accuracy of the model to be higher. You want the way in which the model properly ranks the yes class with a higher probability than the no class to be a higher percent of the time. And that's what ROC is, or AUC. Once again, just realize they're synonymous words. People just use them interchangeably. ROC is the curve. AUC is the C of the RUC. Receiver operator curve, area underneath the receiver operator curve. So that's what AUC stands for. It's this, the ROC is the C in the AUC. With this right here, our part grid, all this good stuff. Let's go down here and let's make a GLM net. This is one of the things I like to point out is that when you learn the caret package or you learn how to use the train function within the caret package, it should be pretty easy to change this right here. If we want to change it over to like a GLM net, so let's go right here. Let's drop it in. We're still using the same thing. We're going to use payplan though. And what we need to do now is we need to make, oh, we already have our GLM net grid. Wow. Okay, perfect. Perfect. We have our GLM net grid, and then we have to go here to tune grid. I don't like that it's looking like that. So tune grid. Tune grid has the, I believe, there we go. And then what do we call this? GLM net grid. That should do it, unless I made a typo. I love copy pasting these, but really? Let's fix that. There we go. Oh, it's because it was all meant to be there. And then let's not overwrite our GLM. Let's call it GLM net. We'll overwrite what GLM net was in there. Error grid should have columns parameter. Oh, ha 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 ha. That. There we go. I didn't change my method. What's your go-to model? Probably GBMs. Probably gradient boosted models. They take more time. Or, you know what? I say that and then Elastic Net. Elastic Net is just advanced regression. So does that make sense, Jordan? Probably Elastic Net because it's just advanced regression. It's literally going to make right here, was it 200 models? So this right here is 11 models, and this right here is, I'm trying to have a hard time thinking of this, 21. Is that right? So 11 times 21 is 231 models. This is making 231 models. So right now I'm making 231 different models, and our best AUC previously was, what was our best AUC? This one was pretty bad, and this one right here. So our best AUC was 72, and this is definitely better as long as this doesn't have a crazy. How does Brian know, as we wait for our models to run right here, how do I know that this AUC, that's an AUC, is better than this AUC? How do I know that this AUC right here is better than this AUC? And the answer is over here. How do I know that this AUC is better than this AUC? I can quickly look at it and I can be like, okay, that's $72, that's $3, that's $66, that's $2. I'm rounding them very, very liberally, but wait, but remember they're significantly better. So Ahmed, you're totally right. 1,000 points, Ahmed. They're beyond one standard deviation. If you run they're exactly the difference, and the larger of the two standard deviations. So if you were to compute this right here, which we can do, here we'll go right here, and we take the difference of the two models, and then we take the larger of the two standard deviations, and we divide, we get more than one standard deviation. And so I was kind of looking at it real briefly right here to say, okay, here's this model's ROC, here's this model's ROC, that's a difference of like 6, and that is more than the larger of the two standard deviations. And this is how I often do things when I'm doing it. Does it make sense that, yes, you can sit down and you can mathematically compute the difference of 72 and 66, and then when you look at 3 right here, it's definitely more than one standard deviation. And when you get used to looking at output like this, so you'd always compare, like, usually you just compare two models, because you would use the larger of the two standard deviations or 3 if you have multiple standard deviations, but I would usually just compare two models. Right now, the one that's winning out, in my opinion, is the GLM. So what am I going to do? I'm going to look at my GLM net results, which I just saved it into GLM lowercase net because I think I have other ones. Oh no. Which one is it? That's this one. Okay, so here's the results of this. And we should have 231 models. It won't print them all. But yeah, it's 231 models. And we might, oof, that model did really bad. Wait, we've got something right here, but that might not beat it out. But let's plot it. Let's take a look. Our best one was what, 72? That's the R part. 72.259. Okay, that's our best model. I'm going to go and grab the results we need with the following code. I'm going to go GLM net, it's the lowercase, and I'll put this up top. So this is going to show me my best out of all of those. It's basically the same. If you look at this right here, it's virtually identical to the previous one. So, and we have these currently stored here too. I'll take this code right here and put it right here. So the output really shows that the regularization of it really didn't change much. The regularization, when you look at this right here, this is like a friend saying, I'll give you $72.25. This is a friend saying, I'll give you $72.41. And the standard deviation of this is $3. So does everyone see it? There's no recognizable difference when we add in the regularization right here. The regularization has like nothing going on. Does that make perfect sense? Like regularization did not help us at all. So what's the next thing we're going to test right here? Regularization, which controlled for the bias variance trade-off, really added nothing to this. And if you look, the lambda is so small right here that the lambda being so small indicates that, yeah, because a small lambda means a small amount of regularization penalty. Who's with me on that? That the small lambda indicates that there was very little to no regularization penalty. Because in regularized regression, we control for the bias variance trade-off, And when you look at this right here, the models that are doing the best have a very small regularization. Look at that. The models that are doing the best have like very small regularization penalties. When you start penalizing for the regularization, let me think. Let me think, Adrian. A really good question. Small regularization penalty. Let me double check my brain. If you have a small regularization penalty, then you will make, I think, fewer mistakes. Because, yeah, that's right. If you have a small regularization penalty, you'll make fewer mistakes because you'll have more variance. Because the regularization penalty right here, the lambda, controls for the variance. So if you increase this, you will decrease the variance of the model. Does that make sense? This is kind of similar. So that was with SVM. So this is how much we're penalized. So small lambda equals higher variance. Yep. Because no, that Ahmed, put that right there. That was perfect. Here, I'll show you mathematically why small lambda equals higher variance. Exactly. You said small lambda equals higher variance, right? That is accurate. And let me pull up the right set of notes to show you the equation, because the equation literally shows it. Or do we show it right here? Oh, that's logistic for them. So what Ahmed said, large lambda, wait, no. Large, here, we can look at it mathematically. So let me get the notes on that. Oh my gosh, we've done so much. We've done so much. Okay, I think this is the right one right here. Generalized by regular regression, cool. So the equation right here, boom, this has got it. Okay, let's talk about this. This is huge for the test right here. Okay, so this right here, well, let's show the big one because it shows both lambda and alpha. Okay, cool. So what are lambda and alpha? Lambda and alpha are what control the regularized. When you see me doing GLM net, I'm controlling lambda and alpha. This grid that I'm making down here in the bottom of this graphic right here, this is my alpha, this is my lambda. Does that make sense? This is the alpha that I'm tuning through, and this is the lambda that I'm tuning through. So alpha can only go from 0 to 1. Now let's look at that. Alpha can only go from 0 to 1 because alpha controls what? Why can alpha only go from 0 to 1? Because just like theoretically, what does alpha do? Like, why is alpha contained between 0 and 1? Like, why would you... That's such a good written test question. Like, why does alpha only go through the values from 0 to 1? Like, it's good written test, which we don't have written tests right now. Why does alpha only go through the values of 0 through 1? Any ideas? Lasso and ridge. It's the mixture of lasso and ridge, because if you look at this right here, 1 would be all, that's going to be lasso right there, because r squared has nothing to do with r squared, but it's the way I keep it in my head. And that's the way we are penalizing ourselves for the coefficient. So if we had 1, this would be all lasso. And if we have 0, we'd have 1 minus 0, and this would be all ridge, and then this would be 0 and be no lasso. So the alpha is the mixing. That's why when you look at this right here, it says mixing percentage, because this is going to be all ridge, and this is going to be all lasso, and this is the 50-50 mix. It's like the Arnold Palmer, the lemonade and iced tea. So you can have all iced tea, you can have all lemonade, or you could have like lemonade iced tea, or you could have like little bit of iced tea in your lemonade, or a little bit of lemonade in your iced tea. So it's the amount you're mixing. Does everyone understand what this mixing percentage is? It's like you're mixing the models together and choosing the amount of lasso and ridge you want in your kind of equation right here. But the amount of lasso and ridge you take is controlled by what? The amount of lasso and ridge you take is controlled by what? The amount, yep, lambda. Yep. And all of everything over here is the variance component. So everything over here this is all variance. And this is the weight of the variance. So that's the weight of the variance. And everything right here is bias. So we've got the bias, we've got the variance. So what is the smallest weight you could give to the variance? What is the smallest weight you could give to the variance? Like when you're trying to fit a model, the smallest possible weight you could give to that variance is what? The smallest weight you could give to the variance is 0. Does everyone see we have 0 on this graphic? Are things very close to 0? The smallest like penalty or parameter cost, hopefully I'm not confusing with terms. That's where we definitely, when I want to make sure we understand like what exactly this means, because we did mention similar words yesterday. The smallest penalty you could give to the variance or weight you could give to it is 0. And so if you do that, what happens to this? If you give it a 0 weight, what happens to it? This model will just try to optimize on what? If you give it a 0 weight, this model will only optimize on the bias, the SSE. The model will only try to minimize bias. So small lambda equals what? Small lambda leads to high what? Once you know one is high, the other is low. So large lambda, reverse it. Because remember, the small lambda, let me double check here. Yeah, it is reverse. Yeah. No. Think about this right here. What is this model going to try to minimize right now? Lambda is very small. High, I think you're right. Vedrina. Let me double check because it's so easy to reverse it. So small lambda equals high variance. Yeah. And we'll mention the one that makes sense. Like the first thing that makes sense is small bias. So small bias, high variance, because it has to be the reverse. And you might say, why is it small bias? It's small bias because, remember, we've eliminated this portion of the equation. So when we do this, small lambda equals high variance, exactly, because we're not optimizing the variance. So the higher the penalty right here, the more we're optimizing on variance. Without this component of the equation, you're only optimizing on bias. And what do we mean by optimizing? So, yep, small lambda equals high variance, exactly. Yep. And because if you have small bias, you have high variance. Like just the way it trades off. And we just did not fit this on the variance at all. We did not take into account the variance, so this is more likely to be a high variance model. Who feels like, does this make more sense right here? That if we were to have a very small lambda, we'd expect the model to have higher variance, but we'd be optimizing on the bias because we're not even taking this into account. The model is only going to try to minimize the bias because it tries to minimize this, and it's only examining the bias right now. Does this make sense to everybody right now a little bit? Like what's going on? And we choose the best base model. Yay, crazy numbers. Yep, got it, awesome. And these are the models here that are predicted to work the best on what? This data right here are the models that is predicted to work best on the what? This data right here is the data that's predicted to work the best on the train, the validation, the holdout. These models right here are predicted to work the best on the train, the validation, or the holdout. The train, the validation, or the holdout. And we did, the ones we picked are kind of the ones that are fit towards bias. Validation. Because this is the right here, cross-validation right here. So these are the ones from the k-fold cross-validation process. How many models do we fit to our holdout? How many models do we try on our holdout? Just what? How many models do we try on our holdout? How many models? Because we definitely tried out 231 models right here. We tried out 231 models. Yep, just one, just the best one. We take our one model and we see if it works. The holdout is just a test. It's like to say, okay, I'm going to pick this model and I'm going to see if it actually works on it. So we can use things like the post resample function, which we can do that right here. We can take, so the model I'm going to pick, the model Brian's going to pick. We could do a GBM too if we want. We could do an SVM too. Once you do this right here, because this is good. This is good stuff we're doing right here. What's going on with that button? What's that? Your device needs to be restarted, doing small updates. Updates! We love updates. So the best, I like it. At this point right here, if I were to stop the process, I'd go to the post resample and caret. If you see it takes the predicted and it takes the observed. Now, one thing you have to make sure you have right here is I need two categorical variables. So I need a categorical predicted, I need a categorical observed. So make sure when you're getting your output from your models, you could do it outside of here. So we compare models, so we compare the AUCs of the holdouts. Not the only time you use the holdout is in your final step. The only time you use your holdout, because every AUC I'm comparing here for these models, every AUC I'm comparing right here are the AUCs from the what's. Every single one of these AUCs are AUCs on what's right now. All of these AUCs are all AUCs on what portion of the data. These are all AUCs on the what portion. Wait, careful, careful. Right there. The validation. The models are made from the training, and then the estimate right here is from the validation. Does that make sense? We make the models on the train, but then we estimate how they will work on the validation, and we get the estimate of how the model will work. So it doesn't report to us how the model worked on the data it was created from. It reports to us how the model is estimated to work on new data, because what's our whole goal? To make it work on new data. Does that make sense? I know it's very confusing. It's like, well, wait a minute. Why don't we just say how the model works on the data it was created from? Well, it was created from that data. So let's use the estimate of how the model is expected to work on new data, because the goal is to get the model to work on new data. So we do this where we make many models. And this is what's so beautiful. And I love statistics. I love it so much because someone who didn't know statistics could say, wait a minute, Brian, you're telling me you just made 231 models and you picked a model. Didn't you just kind of like search for results? Didn't you just kind of like, you look at the Tyler Vigen site, I think that's his name, where he can show you spurious correlations, where he can show you things that just happen by random chance because we just look through too many variables. If you look through so many variables, you'll eventually find something. Someone could say, Brian, you looked through hundreds of, maybe even thousands of models. How do you know your model works on new data? Maybe you just found one and got lucky. How do you know your model actually works? How do I know? What would I say to that person? I'd say, aha, I have a what? I have this to know it works on that data. I have this not on that data, but on new data. How would I know my model actually works? Not because of the validation. The validation is an estimate, and the holdout is my proof it works. Holdout's the test of it. So good. No, there's good stuff right here. Keep you guys again 1,000 points. I'm in Jordan right there, and Anisha and Madeline, because the validation is how we pick the model. So I'm going to pick the model over here because I think it'll work on new data. But then I take this. And what do? I go down here and let's get the predicteds. So I'm going to make some predicteds right here. I'm going to go to predict, and we're going to take the GLM net. And I think it just takes the best model. Let's see here, GLM net. And so we should go, is it new data? Every once in a while I forget is my holdout called my holdout on this? Should be called my holdout. Okay, cool. Let's look at the predicteds. We might have probabilities. We do have probabilities. Is it type? Hate it when autocomplete doesn't jump in. Could save it as, what is it? Is it type? It's type, isn't it? Type equals prob. Yeah, there it is. And then that's right there. So let me go to predicteds. There's so many things to remember. It's just like, wait, what? Error. Type equals probs. It doesn't like that. Type of probs. Here we go. Oh, there's your ROC right there. So we could just take predict, R part, new data equals this, hold up purchase. Is not. Let's see right here. What did I make a mistake on? Because we've got the right code. Let's grab these. Predicteds. Let me look right here. Okay, predict, and we're using our GLM net. Should like the GLM net on this, right? Let me highlight this part of the code. We are getting the probabilities out of that. We don't want the probabilities though. And let me go to the GLM net. Type equals prob. I thought it was type equals prob. Let's just see it here. Once again, code is stumping us for just a moment. Type equals probs. GLM net. What is going on? Well, 2 seconds here, everybody. Predict GLM net, new data. You get 1,000 points of help, Brian. I think you saved it as GLM. Oh, did I? I've got Oh, you're right. Oh my gosh, is that the issue? Let's see. This is what happens when you start off with too many codes. Must have the same length. What we have going on, let's look at the predictions. Okay, good. Wait. Oh my gosh. Jordan. 10,000 points, Jordan. Literally, I have too much going on right here. I have too much. See, that's when you're like, I thought it would work because we have right here predicteds. Now we got the predicteds. Cool. And then hold out purchase. Oh, we're not using purchase. That's going to be an issue. Okay. So literally all it was is I went to my wrong model. Everything I coded was correct. Went to the wrong model. Things went haywire. Just got, if you look at all the GLM nets I have in here right now, I have GLM, all of these, and then I have these objects. I have GLM with a lowercase n, capital N, and then all capital. And you shouldn't have this much in your R. That's a bad idea. So that created problems. If we look at the post resample function again, we need in it predicteds and observed. So what are going to be our observed values? Well, we need to go here to our holdout and $y, and we're predicting pay plan if I remember correctly. Now, one thing you want to make sure is that this is a categorical variable. So we call this observed right here. This is just kind of breaking down the code so we can look at it. And I don't know if that's a factor right now. I'm going to store it as a factor. I think you might need this for the take home. Why I wanted to do it this way, because I think, yeah. Okay, good. So post resample should work now. Predicted, observed. There we go. That's got it. And PROC should do it also. We go to PROC. Where's my PROC? Oh. Library, PROC. And let's go here. So post resample. Oh my gosh. Post resample. It's ROC. That's what it is. The library is PROC. So many random codes to remember. Pay plan. Do not hop around as much as Brian is hopping around. What does kappa tell you? Kappa is how well your model does compared to a random guess model. Do not worry about it. It's kind of the percent increase improvement over the random guess model. We can definitely take a look at that because I do want to mention it because you might see it in like another discipline. So let's go to ROC right here. With the ROC, we're just going to put in, I believe it has the order predicted and observed. And I do like, I'm going to show one last thing right here. Does it have the reverse order? We'll fix this up here in a moment. Let's talk about kappa for a moment. Not on the test. Must be numeric or ordered. So we need the, we need the probabilities. What am I doing? So we have to do type equals prob for the predicteds because it does need capital P because it needs the probabilities. So prob, there it is, lowercase p. So many lowercase, and there we goes that. And we need the column of the yeses. So the yeses, I believe, is it's the second. So we need the second column right here. And that's got the predicteds. And I think we have it in the wrong order now. Up, what is going on? There's the predicteds. We'll look at this here in a moment. So to interpret kappa, let's just look at it real briefly right here. We'll have it in the categorical models. I'll go back to that here in a second. But with the kappa, where do we have kappa at? We should have kappa with logistic. So let's go to kappa real quick right here. So logistic. Let me see here. Chapter 6 logistic, classification with logistic. Here we go. Okay. And let's talk about kappa real briefly. Cool. Kappa, kappa, kappa. Here we go. So when you look at kappa, which we will not interpret, and you might say, Brian, why don't we use kappa in this class? I'm not a huge fan of it because we already have accuracy and we already have AUC. I personally like AUC the best, but kappa is not a horrible metric to use. Well, you should only use the holdout one time. You should only use the holdout one time because as soon as you start putting multiple things on the holdout and picking by how everything works on the holdout, what might you be doing? As soon, and then when we're testing to see if one model should be preferred over the other, how do we compare two models that don't both use the RMSE? Compare the AUC. Compare the AUC. Does that make sense, Phaedrina? If you don't have RMSE, you'll use AUC. So in our models right back here, we would compare the AUCs of these models right here. And since we don't have RMSE, we're just going to compare the AUCs. Like here's this model's AUC. And then we're only going to pick the best one to use, or one within one standard deviation of it. So what if one is RMSE so they wouldn't be. Why would one model not be RMSE and one model not be AUC? Why would one model, and if we're comparing these two, we need to use this metric. Why would, and they have a very small difference. Yeah, and so because you'd be comparing two different things, you'd be comparing a model that explains like the usage, which would be quantitative, and you'd explain one that would be like pay plan, which would be categorical yes, no. So you can't have a model that is one, you wouldn't be, they're two different models. It would be apples to oranges. So the models would not be predicting the same thing. You could say one's kind of better in terms of AUC, but it's like saying, is a baseball player better than a football player? And it's like, it's two different sports. Like which player, like who's better, LeBron James or Ken Griffey Jr.? You're like, well, wait a minute, it's two different sports. You'd be like, well, Ken Griffey Jr. hit more. Imagine if someone said this: Ken Griffey Jr. hit more home runs than LeBron James. You'd be like, well, yeah, it's two different sports. You'd be like, well, LeBron James has a higher free throw percentage than Ken Griffey Jr. You'd be like, well, yeah, you can't compare them. Does that make sense? Like RMSE is like home runs, and AUC is like free throws. So they're two different things. Yeah, you're gonna suck up with LeBron. I like that right there. So right here, when you look at what kappa is, I think the equation kind of makes more sense to it. It's kind of the percent increase over the random model. Now we look at how the model would do with like a random guess. Do not worry, this is not on the test. So don't be like, oh no, Brian didn't tell us this. I didn't tell you this. But what kappa is, it's going to look at the accuracy of a random guess model here. So the computations right here are completely computed based on how we would do by a random guess. You can kind of go through here and think about if the model's like all one class, then it would just, predict everything to be actually what it is. And we would have accuracy very high if everything was all the same class. So this is a random guess model, and that's what we're going to use as the bottom metric right here. So what is the bottom of this equation? The bottom of this equation is like what is left from the random guess model. So if the random guess model were to do very poorly, this would be very large. If the random guess model did very poorly, this would be a large number. And if the random guess were to do very good, this would be very small. So the green indicates that the random guess did very well. So this is kind of what's left to explain out of the random guess model. And then when we look at our model, we're going to compare a difference. So think about this. All this is, the kappa, is just a difference whatized. And it literally goes back to observation minus mean over standard deviation equals z-score. All the kappa is a standardized metric to explain the difference between our model and the random guess model and how much more it explains of the leftover variation. So what you would want the kappa to be, if your model does really, 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 really well, you'd want the kappa to be 1, because think about this. This is how much is left to explain, and what is the best accuracy our model could have? What is the best possible accuracy our model could have? What is the best possible accuracy our model could have? What is the best possible accuracy our model could have? The best accuracy our model could have is what? Kind of, pretty much, like theoretically kind of that, and in this instance it'd be 1. So the best accuracy our model could have is 1. And if this is 1, if our accuracy of our model is 100%, then what would this solve out to? What would this, it would solve out to, and it would also solve to 1. So the kappa here would be 1 because our model explains this much of the remaining percent of variation left over from the random guess model. So, or the accuracy, this much more percent of the accuracy left over by the random guess model. So the bottom part of this is like the remaining leftover accuracy not explained by the random guess model. But think about this. What is kind of the lowest kappa could be? The lowest kappa could do worse than this, but it'd be really bad if it did. Our model could do just as bad as what? Our model could do just as bad as the random. Isn't 1 impossible because the denominator would be 0? Because the numerator. No. Because here I'll explain. Let me explain detail on that. Here, let me explain it before I do the next thing. So what it is you look at how the random guess model does, which this just computes a random guess model right here. Like you run through this, like we won't solve this by hand ever, and we're just managing kappa here for a second. But this right here computes how well a random guess model does. And so when you compute this bottom number right here, this bottom number right here will compute out to something like the random guess model. The accuracy of the random guess model was something like 70%. The random guess model was 70% accurate. So how much is left for the random guess model to improve? How much is left for the random guess model to improve? That is solved with this. So the bottom of this equation is how much is left for the random guess model to improve. And the random guess model could improve by this amount because it's that much off from a perfect model. So the random guess model could improve by this amount. So what if our model was perfect? Remember, the random guess model had an accuracy of 70%. So the random guess model had an accuracy of 70%. And if our model was perfect, then our model would have an accuracy of what? Our model, the model we create, would have an accuracy of 1.00. Now, what would this equal out to? That would mean that we explained or we accounted for all the remaining accuracy that the other model did not. And we would get 0.3 over 0.3, and we get the highest kappa because our model did what the random guess model could not. It got an accuracy of 1. Now, going just a tiny bit back here, what if our model is just as bad as the random guess model? So what if our model is just as bad as the random guess model? Our model would have an accuracy of what? If our model was just as bad as the random guess model, it would have an accuracy of what? Our model would have an accuracy of that right there. And then what would this equal out to? Well, this would equal out to 0. And then we'd get a kappa of 0 to tell us that our model didn't do any percent better on the accuracy than the random guess model for the remaining portion. It has to do with the remaining portion of variation or the remaining portion of accuracy unexplained. So we would get a 0 there on the improvement over the random guess model, and we'd see this. But think about this. What if our model had an accuracy of 85%? What is the kappa here? Who here can solve for kappa? 1,000 points. First person who here can solve for kappa, and hopefully this will make sense when you see it this way. Who here can solve for kappa right now? What is kappa right now? The kappa now would be 0.5. And so when you think about what that means, it means in terms of how much better the random guess model could do on the accuracy, our model was able to obtain 50% of that improvement. So it's an improvement upon what is remaining from a perfect model compared to the random guess model. So the bottom part of the equation down here is what is remaining in the accuracy from the perfect model, and then the top part up here is the amount we get from our model towards the perfect. Does that make sense, Anisha? It's looking at how our accuracy does compared to what the random guess model does not do. The random guess model does not, in this example, account for 30% of the accuracy. It's off by 30% of a perfect model, and our model is able to obtain 30 or 50% of that 30% accuracy we're missing. So it explained over above the random guess model. Pretty much that's it. It's like, if you really abbreviate it down very quickly, you might say like it's a comparison to the random guess model. I would say that it's a comparison to the random guess model and about how much better we do from it. Like it shows about how much better we're doing than a random guess model, but it's not like the percent better we're doing. It's the amount of accuracy we obtain that the random guess model is not obtaining. So we obtain, in this instance, 50% of the accuracy that the random guess model is not obtaining. So here's the definition I can best give for it, I think. The amount of accuracy that our model obtains that the random guess model did not account for. The amount of accuracy our model obtains that the random guess model did not account for. And in this instance, our model obtained 50% of the accuracy that the random guess model did not account for. The bottom part of this is the accuracy the random guess model does not account for, and the top part of this is what we obtain from this. So it's the amount of accuracy our model contains that the random guess model did not account for. See, now I want to put it on the test now. See, that just sounds more confusing. I've never loved kappa. Sorry, kappa. Sorry, kappa. Sorry, Twitch. Sorry, kappa. But I've never had a big. It's to me, it's a little bit more confusing. But you do see it. Kappa's used. And kappa's in output. So it's not bad to know. It's not bad to know. I just don't use it. You're welcome, Nisha. Thank you for the question. That's what we're here to do. Because do you see kappa in what you do, Anisha, with public health and everything? Do you see kappa used? I mean, if you do, if it's all right. I mean, knowing these things is important because you'll see it in lots of different things. I can't control what people will use. I have my preferences and I have the things I like to explain, but I can't control what every discipline will use. I was looking at some reports yesterday and I was like, why? Ah, cool. Yeah. It's comparison to random guess model. Yeah. On our improvement with the remaining portion of variation. Yeah. And so, yeah, it's used a lot. It's used a lot. What other big ask questions? Who's got a question right now? Really good questions. Oh, what was your question again? Yeah, let me do it. Ahmed. Ahmed asked, wait, Ahmed, you might have to repeat it. Oh, wait, here we go. So wouldn't it make sense to compare the best results of different models by how they generalize on the holdout? Good question right there. The reason we would not test everything on the holdout is because then you would be basically picking based on the holdout. Imagine, because you could do this. Imagine you were to go here, and you guys know my favorite sites. I've got so many favorite sites. Let's go to one of Brian's favorite sites. Let's go to method in caret package. So we're going to the methods in the caret package, and you go here and you try out, you make 100 different models, which look, you got all these can be done with classification. Let's just see how many times classification appears in here. So just, we'll pretend it, you make 193 models. Now, if you were to test this on your holdout, you would have then tested 193 models on your holdout. And they're literally telling you categorical, quantitative, categorical, quantitative, categorical. Love that they do this with this. And so you could make 193 models. That's it right there, Jordan. Jordan, that's exactly it. Because if you put your model 193 times on the holdout, one of those models might work by random chance. And this is what we do. Like, we haven't even talked about family-wise alpha in this class, but there's things like family-wise alpha control for multiple tests. And this is where, unfortunately, we see like misuse of statistics, because the whole point of the test is to give it one try at it. The whole point of the test is it gets one shot. And if it works, it works. Because what happens when we repeatedly try something? Because watch this. If I were to run 193 tests, let's do this right here. If I run 193 tests, this is a really good for loop question. So, well, it doesn't even need a for loop. You could do it with a for loop. So we only use AUC RMSE of the holdout to see if we overfit. Yes, that's how you tell overfitting. Yep. And watch this. You ready? I'm going to do the following. I'm going to go here, and let's make a model. And this is going to be a linear model of y. Let's do this. Y is the vector of 1 through 100. X is random normal numbers 1 through 100. Anything, or 100 random normal numbers. Anything we see between y and x should be completely due to what now? Any relationship that x and y have is completely what? Any relationship they have is completely and utterly due to what? You know my favorite word. You guys know it. It's going to happen. Fourth time today. Anything we see due to them is completely by random chance. You got it. Anything right here is completely and utterly random. It's playing the music, right? You guys hear the music, right? I hope so. So you like play it. You got it. We could play right there. We got the wolf in there. You can't. Monster Cat needs to see it. Corroborative time. I played longer. See if I know Monster Cat will come after me. Monster Cat, the cat's coming after me. And so what I'm gonna do now is I'm gonna store this summary into m.sum, because then I can manipulate it. And I'm gonna take from this. You know what? Wait, is it not? Where is it? Can I not just do RMSE? It's such a bummer. Terms, residuals. Oh wait, so that's the residuals. Okay, you know what we gotta do? Oh, but then I can't. Can we get the p-value on this? Can we not just get the p-value? RMSE. Let me look here. 2 seconds. Coefficients, sigma, r squared. Let's see here. How to get p-value. I just want the p-value. You know what I can do? I can go here to correlation. And that, oh, run. There's the correlation. It's not giving me the p-value? 10,000 points, first person tell me how to get the p-values out of these. I don't want to work that hard to get that p-value. Core.test. There we go. All I want is to save the p-value. m.core. And let's look here. m.core, $ p-value. Done. P-value obtained. Cool. That was my whole goal of this, is to get that p-value out of it. And the p-value of 0.56 will be the same. It should be the same as the regression model. And here's the p-value. So if you see the p-value of the regression model of 0.561, it's the same p-value down here on this. So all we're doing is just getting the p-value of the regression or the correlation. Same thing going on. But watch this. What we're going to do right now is we're going to do the suggestion of making 193 tests. So what we actually have is everything we're seeing here is random. Like this, by definition, it's random. Like that's random data. So we're going to take and we're going to store a vector of test. Test will be a blank vector. And then we're going to go here. We're going to put a for loop. And we're going to take this. And we're going to take our data and we're going to put it inside of here. And then we're going to go to test. We're going to put this here. We're going to put an I right here. And we'll run this variable I through vector 1 through 193. And I think that'll do it. That did it, it looks like. Cool. These are all p-values. And the lowest p-value we obtained by random chance was 0.0003. If you see this p-value in your research, who here does research? If you see this p-value in your research, are you excited? Are you like, yeah, oh man, 0.0003, that's awesome. Oh my gosh, whoa. Would you be super excited? I'm so glad. That's a pretty low one for what I thought would happen. Would you be super excited if you saw that? For anyone who does like research and knows p-values, would you be like, whoa, 0.0003? Oh man, I'd be like, whoa, we hit the jackpot. You'd be like, this is awesome. We did some awesome research. Man, we did a great job. How was this 0.003 obtained? Say it one more time for me. We got to do it. Monster Cat, you can't have this channel. Not today, Monster Cat. How was that p-value obtained? How was that p-value obtained? Woo! Can't turn around. I was going to spin around the chair. P-value is completely obtained by random chance. You could, we could repeat the process. That 0.03, you see that one's not as low. I was shocked we got 0.003. Did we get, how many O's did we get? Did we get 3 O's? We got 3 O's. I was actually shocked it was that low. When I saw 0.003, that was even lower than I thought. The first time we did it, you see, other times we didn't get as low as ones. That, I'm shocked it's that high. But that 0.000 with 3 O's, I was really shocked it was that low, but it was completely by random chance. Kind of cool that we had something that low by random chance, because that's really, really uncommon, but it was by random chance. Completely by random chance. And that's running 193 tests. So the more tests we run, that's why we only do it on the holdout one time, because we don't want to get lucky. You know, does that make sense? Like you don't want a low p-value that's by random chance. So if you do a bunch of tests on the holdout, you might find one that works on the holdout, but then as Jordan was saying, it might just be overfit to the holdout. Like you might have one that works on the holdout, but it worked by random chance. So we literally save the holdout. Think about this. Okay, wait. Like I love cooking. I love cooking for my fiance. And I'm going to cook. One thing I want to try to cook again is calzones. Calzones are amazing. Dr. Paolo Latti's, he's Italian in our department, cooks the most amazing calzones. And there's so much good food. Like, try out everything. Try out all the food around the world. You know, just it's Brian's life advice. Life advice with Brian. I mean, no, calzones are not like the most, but try a calzone cooked for someone who's from Italy. Holy moly. Oh my gosh. This is Brian talking about Dr. Paulo Latiz is amazing. I mean, he's a doctor in, in business and analytics and all that good stuff. I'm trying to think what his doctorate's in, but has anyone ever had like real Italian, like, I mean, I've been to Italian restaurants. I've been to like real Italian restaurants, but having home cooked Italian food, holy moly. And you guys know I love like Soccer Taco. There's other, and Vadrino was telling us some good places. And let me shout out another place in Knoxville, because once restaurants start opening, if, once again, don't just go crazy and spend all your money. But Taste of Thai is one of my favorite places. Taste of Thai. Has anyone ever been to Taste of Thai besides me? Taste of Thai is amazing. Stock and Barrel Burgers is amazing. Hard Knocks Pizza is amazing. You can shout out your favorite restaurant here in Knoxville if you got a favorite restaurant. Taste of Thai is absolutely amazing. So I love Thai food. Yeah, some pad ki mao or tom kai gai. But sticky rice cafe. Yeah, no, it's so much good stuff. Like support local businesses. I agree 100%. Like Surin of Thai is good also. Surin Thai, that's awesome. We haven't been there. Lonesome Dove. I've heard of Lonesome Dove. You definitely support. Support every business you want, but I'm a big fan of local businesses. Like Taste of Thai is there's only one Taste of Thai as far as I know. If there's another restaurant called it, was this La Herenda Taqueria in North Knox, has great street tacos. Ooh, that sounds really good. Lonesome Dove, Pete's Cafe. Yeah, Pete's Cafe near downtown. Really great local place right there. Lonesome Dove, super bougie. Right there. So much fun. Yeah, and so when we think about this right here, what was I talking about? I just started thinking about food because I just get hungry midway through class. But the rattlesnake and rabbit is so good. Rattlesnake and rabbit. Oh my gosh. Asia Kitchen. Oh, that sounds good. Stefano's a big classic. Stefano's on the Strip, right? Stefano's Chicago pizza, right? Really good. And Sylvia's, where's Sylvia's at? I'm trying to think. I've forgotten where everything's at. But support local businesses. Try new food. That's just Brian's life advice. Like, I think the more we try new things and the more we experience. Oh yeah, we're talking about the calzone recipe. That's what it was. He actually gave it to me. He explained it. Oh, that's what I was going to explain. Okay, I got my example back. Ishan, 1,000 points. Okay, so Ishan brought us back on track right here. So Brian's going to cook a calzone for near Publix. Oh, it is, isn't it? Okay, I'm leaving soon. Okay, so I should try that. I should give it a try. It's a Mexican place. Should give that a try next to Jimmy John's. Okay, I know where Sylvia's at right now. But yeah, and that seems like it's a local place too. So local businesses, I really like all the local restaurants. Nothing, I mean, I worked at Cheddar's, so I have nothing against chain restaurants either. But it's just like, I don't know, it's more fun. Balter's Beer, is that Balter's Beer? I think they're good too. Man, I'm gonna miss Knoxville. I'll be back every once in a while, but there's so many cool things in Knoxville. So many cool things. Shout out to Knoxville. Okay, Brian's gonna make calzones for his fiance. So with calzones made for my fiance, think about this. How many times does Brian get to test serving the calzone if he's like tonight? And just think about this. If I make a huge mistake, we're not making calzones again. What is the real test right here? The real test is done how many times? I mean, you could make them like every month or something like that. But when you think about it, the real test is when you make the dish, like when you actually make it. So when you think about how we choose our model, we validate our model and we pick the one that we think will work the best. When you test the model, you only do it one time because you only get that one test on it, and you don't keep testing it many times. It's kind of like taking the SAT. When you take the SAT as a practice test at home, is that you're training, careful, I know it's going to sound like that's not the answer. When you take the SAT at home, is that you're training your validation or your holdout? Is that you're training your validation or your holdout when you take the SAT or GRE or MCAT or PCAT or GMAT? When you take any test at home, is that you're training your validation or your holdout? It sounds like training, but I would say it's more validation. I guess like the taking of it, the test itself, it's kind of it's like a training validation thing. Like I know thinking about these things theoretically sometimes is a little hard to do because there's not a k-fold cross validation in this. So someone could argue it's actually training, but it's either the training or the validation. because you are learning from it. So you can say, okay, I'm learning from it, so it's training. But you are getting an estimate of how you'll do on the test when you take it on that day. Does that make sense? If you think about it the way of I'm learning from the SAT, then it's training. Like I'm learning how to take the SAT, that's training. But if you think I'm getting an estimate of how I will do on the test, that's the validation, because you're getting an estimate of how you'll do on the test. Now, our estimate comes from the k-fold cross-validation process, so it's a within the training sample. So then when you take the test on the day, that's technically the what. Because think, those questions you've never seen before. They've been what from your model. When you take that test that day, you want to do what? Ooh, I've got a good test question. I should have wrote this. When you take the test, that's actually the what, because you never see that data till the day you take it. And it all makes sense, because I'm about to give it the holdout. What if we have someone take the SAT? Oh, you see, you can totally do this. You can totally run this right here. The SAT has scores that are normally distributed with a mean of, I wonder if I could get it to round this way. So we're going to try something right here. We're going to do SAT scores. The SAT has a mean of, what is the mean score on the SAT? Is it like 500 per section? So it'd be 1,000. So if we look at the SAT scores, they're going to be normally distributed with a mean of 1,000. And so we could do, I have an idea for this. I have an idea that works. No, they go up by tens, I think. So you can only make like a 510, 520. So this is going to look very, I don't know. Mean is 1059. Cool. Let's do that. Normally distributed, random norm. I cannot type. And random norm works. Why am I breaking on how random norm works? Random norm is how many observations do you want? So we're going to take the SAT 30 times. The mean, we're an average student. And do you know what the standard deviation is, Ishan? Is standard deviation like 50, 80? What's the standard? Let me think right here. It's 1059, and that's 500 away. Standard deviation should be about 120. Is the standard deviation about 120? Ishan, help us. Then they rank students on how well they do on the test. Yep, exactly. I'm thinking it's about 100 or 120 or so. I'm going to say 120 unless Ishan comes back to us with different results. So here, you can see your results, and you can just store this as results. And you could go here to max of results. And whoa, holy moly. Wow, Ishan might come back to us. This is so crazy. And we got super lucky. We're getting the weirdest, randomest. Oh, that's the rainbow button. That was random. We're getting the weirdest, randomness, luckiest results we've ever seen because, I reran the results right here. So we didn't even see that 1400 because I was like, where is it? If we look at the results right now, there's the results, and we have a result right here. And we didn't even get a 1300 result. We jumped straight to the 1400s. How is this result again obtained? Randomly. A person who is an average student, due to the variation in the SAT, taking it 30 times, obtained a 1400 by random chance. They were a perfectly average student, and they obtained a 1400 by random chance, which would be very good by random chance. If I got the standard deviation right, that is correct. Now, if the standard deviation is way smaller, then it would change this result. That 1400, we're just getting the weirdest results first because we don't even get, we haven't seen a 1400 yet again. Oh, there's a 1451. But now they're taking it 30 times again and 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 again. But you don't get to see this. So Ahmed, is it making sense why we don't repeatedly test things on the holdout? Because what could happen if we repeatedly test things on the holdout? We could get lucky. And by lucky, in our terms, that means we overfit it. It's like we're like, wow, we did so well. But in truth, we don't actually do that well because we just keep attempting. Because if this student got the, how many attempts do we have? They get 193 attempts at the SAT. This student gets 193 attempts right now. 193 attempts. So this student gets 193 attempts. Ooh, they didn't even do better than the 30 attempts. They got a 1400. That's good, but it's so weird. The results you can get by randomness. See, look, they're not getting... Wow, that 1400 is pretty rare. And Anisha's right, we might overfit. So the reason we only test it once on the holdout, and this is, if I can't stress these things enough today, it's the idea of when we have a holdout, it is specifically used to do it one time. And guess what? That is how the student does. Are you shocked by that? Are you shocked by how the student did right here? Look at when they got 193 attempts versus when they got 1 attempt. So here's where they had 193 attempts, and we're like, ooh, this is how they do. But here's where they get 1 attempt, and look at how they do now. They do kind of what we'd expect them to do. They're close to the mean, because there's variation in how they'll do, but we don't see something that is higher because we have an unlikely chance of getting a rare event. We could, you could say, well, couldn't it be possible that we overfit? You see, we just got 1,300 and we just got a kind of low score. But usually, because we'll get something closer to the mean, like just the way mathematics works, we're likely to see the truth and you'll get numbers that are closer to the mean. You can keep doing this till you see a weird number. You're like, aha, 1,300, Brian, or this one's low. But if we do it again, see, I'm like, no, that result's not the one we want. But you see, most of the results are going to be very close to the mean. It's very unlikely to get a result that is very far away from the mean, and you only do this one time. I know I am doing it repeatedly, but it's the idea of, okay, we're on this step where we look at our holdout and we see how our model does. Who has additional questions? That was a really good question, Ahmed. Ahmed, another 1,000 points. Thank you for asking. The holdout serves a very important purpose. The holdout is only for one test on our final product. We take our final product and we test it on that, and we say, how does it work? If we repeatedly test on it, we could easily overfit on the holdout, and that'd be very, 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 very bad. We don't want to repeatedly test on the holdout. Who has questions? What I'm saying is, if we take the values of the AUCs on the holdouts from different models and see what model did the best. Well, no, it's the problem though. You're seeing which model does the best, so you're comparing multiple AUCs on the holdout. So because of that, Ahmed, what you are asking is the exact question I thought of. Like, why don't I then just take all my best models from like my validations? Like, okay, here's my best GLM-net, here's my best GBM, here's my best support vector, here's my best neural net, here's my best discretization model. Like, we've got models we didn't even cover. Here's my best spline model. Here's my best compensable component analysis. We've got all these different models we could use. We've got so many models. But then the thing is it's like lottery tickets. Now, what should happen when you play the lottery? What is supposed to happen? What is the naive model for the lottery? This is a review topic now too. The naive model would predict what for you winning the lottery? What's the naive model? The naive model would predict everybody what's the lottery. The naive model would predict, but wait, so what would it predict for everybody? Not winning. The naive model would predict you don't win the lottery, because that's the most common occurrence. So the naive model predicts the majority level for everybody. It says you play the lottery, you lose. Well, will anyone win? No one will win the lottery. The naive model would say no one wins the lottery, because that's the majority level. And so with this in mind, you think about this, that if you take 8 or 9 models, probably exactly, there we go. Classic probability stuff right there. Great job, Nitin. 1,000 points, Andrew, Nitin, Jordan. Thank you for everyone paying attention, because this is something, Ahmed, this is why I'm going so in depth on this, because this is something that I thought a while ago, and I was like, why don't we just take all of our models that have kind of made it to this point, like, okay, we've narrowed it down from this many models to this many models. Each of these maybe 10 models we have now is a lottery ticket. And you know what we don't want to do? We don't want to win the lottery. Every time we test a model on the holdout, we could win the lottery. I know you're like, but Brian, don't I want to win the lottery? You're lucky if you win the lottery. It's something we shouldn't do. We shouldn't get lucky with our model, and our model should not randomly work on the holdout. Every time we test a model on the holdout, our model is being fit to the holdout. And if we repeatedly test models on the holdout, we might find the model that's overfit to the holdout. Because you don't fit your model to the holdout. Because if you select the model that works the best on the holdout, you've now fitted to the holdout. And so, like, you could argue, well, yeah, no, you just, here's what I would do. And Ahmed, you bring up a really good point. So let me say this, Ahmed. What you would do, and here's what I think you should do in practice. Maybe this will make sense. You're going to pick your model that works best on the validation, which is your estimate. So when you pick your model that works the best, Let me write this down in steps, and I think this will make sense. And Andrew, I think I'll answer your question next, Aaron. We got this. So step 1, pick model that works best on validation. Step 2, test it on holdout. And then let's go here. Not overfit, use this model. Overfit, ... Works. So here it is right here. I think this might explain kind of the process I go through. You only get the one test on the holdout. Now, you don't just throw away everything you've done if your model doesn't work on the holdout. But if your model works the best on the holdout, that's the model you use. Yeah, underfit is when it works way better on the holdout. And you'd probably see that for high variance models. It could be a concern. That's a really good question, Jordan. That's a really good theoretical question, because why is our model working so much better than we expected it to? And that's going to be a high variance model. So that's going to be a model that probably took out little bits of information. I would probably, Jordan, that's such a good complex question. Here, I've got Andrew's question next. I would look at the structure of my holdout. You could have an outlier or something extreme in your data that's kind of fitting really well in the holdout. So you could have some sort of outlier that fits really well in the holdout, or your training data could have an outlier that's destroying the training data. So structure of data is very important. Like, it's all about data investigation. Like, maybe my training model has an outlier that is making it do way worse. And so you probably wouldn't see this in things like accuracy. You would see it in RMSE. I'd say RMSE more likely, just as I think about it, could be underfit, because you could have an outlier in your training that's drastically increasing your RMSE. And then in your holdout, you do way better. So you see that the holdout does better because it does not have an outlier drastically changing the model. But also that outlier is going to change the model. But so yeah, you just get interesting things. No, so that's such a good, like, if that was a test question, I had to write an answer to it, I'd be like, I could write a page on this. Oh, no, thank you, Ahmed, very much. And here we'll do Andrew's question next right here. So for those wondering, you pick your model that works the best, you test it, and then if it doesn't work, where it's overfit, you go back to the drawing board. So you take the next best one. So you could say, Brian, aren't we testing more models? But we're doing it algorithmically. We're not testing every model and picking the best one to hold out. We're picking our best model, seeing if it works. If it does work, awesome, we're good. That's our model. If it doesn't work, we go back to the drawing board and we pick a new model, and then we test that one out. It's kind of like the idea of the calzones again. I get to make the calzone for my fiance, and if she likes it, good. That's my calzones. We're making that type of calzone. And if she doesn't like it, I go back to the drawing board, and then I get another test of a model. I don't make her every calzone. I'm like, here's the 100 calzones. I want you to try them all. I go and make, one, try it, good. I just want to make calzones. And Andrew said, I was so close to winning when I was 11. How are you playing lottery at 11? I got 3 numbers right, but I switched the Powerball with another number. I would have gotten 4 numbers in the Powerball. Andrew, if you had won the lottery, you wouldn't be here. If you had won the lottery, you wouldn't be here. I mean, you might. You might be like, we could be like, that's Andrew Wind. The Andrew Wind who's worth $400 million. I tell you the truth. I don't know I know everyone says this, like, I wouldn't want the lottery money. Like, really? If I won the lottery, this is Brian's kind of calzones for everyone. Ahmed, that's awesome. Do we pick the second best model with one standard deviation? You would just, so every model that is within one standard deviation of your best holdout is considered identical, basically. Like, we don't know which model is the best, because remember, standard deviations or standard errors are uncertainties. You've probably heard me say that a lot for 320, or I say it sometimes to you guys, that standard errors or standard deviations are uncertainty. And so any model within one standard deviation is basically like, well, I don't know which of these models could be better. And so you might have a preference. It could come down, Jordan, to preference. If the GLM net and the GLM work about the same, you might pick the GLM, especially if you have to kind of explain to someone what you did. GLM net versus GLM working the same, you might pick the GLM, just because it's easier to say, I just did regression. Like, oh, I just did regression. The person will be like, oh, I know what regression is. Instead of you saying, I did a lasso net regression, which controlled for the regularization and the bias of the model, they'd be like, what? You did an elastic net regression or a ridge lasso? What's that? So if they work the same, you might just be like, hey, I used regression. They're like, oh, cool, I know regression. But if things like the gradient boosted model work better, you might just say I did it all depends. And if everything's within one standard deviation of each other, if the models are all similar, then you can just pick the model you like best and you see if that works on the holdout. There's no, and it's in the notes somewhere where it says like there's no compelling reason to pick any model over another. If they're in one standard deviation, it's all preference then. It's just your preference. If I were to win the lottery, speaking of calzones, you evaded my question of your secret recipe. Oh, well, I don't have the recipe. Ishan, I'll have to get it from Dr. Paulo if he'll let me share it. Ishan, really good question right there. I do not have the recipe. He told me it's all about making the dough. But you see, here's the, when you think about the components of a calzone, the variation in a calzone, because we can bring this back to statistics, you've got a few sources of variation. I've heard even the water, because the dough is going to have variation in it. Like there's variation in the dough. So what makes a good calzone is you've got variation in the dough, in the sauce, in the meats, and in the cheeses, and probably the spices. So you have to isolate those variation and figure it out. It's a secret recipe that I don't even know. So you have to figure out what sources of variation you have. You've got oven variation. You've got preparer variation. Because think about this. Dr. Paulo could give me his recipe, which he kind of has already. He could give me his recipe, but I won't make it as good as him because there's variation from the person making it. And this is how I think of the world statistically, is I think about, okay, what's the variation that goes into making a calzone? And it would be, who's making it? What are the ingredients? Where is it being made? If I've got a brick oven, if I've got a conventional oven, if my oven has a timer, all these things right here. So what is the variation that goes into the calzone? And probably a big source of variation is the person. Like you could give me the exact same ingredients, the exact same equipment that Dr. Paulo has, and I probably won't make as good of a calzone because there's a lot of variation between individuals. So that's what we try to focus on right here in statistics is we're like, okay, where's the sources of variation and what do we see for the differences? I think we're pretty much done. I know we're done like 4 minutes early, but are there any last questions? Feel free to ask questions away. Crabby Ice Secret Recipes. I'm working with GLMNet and I'm getting a weird error and I was wondering if you could tell me what it is. Yeah, send it to me, Adam. What is it? What is the weird error you're getting? And definitely check, because I can say things publicly about, make sure you have the right fit control. Make sure like there were missing values in resample performance measures. There are missing values in resample performance measures. Make sure like your train and your holdout are put properly. Make sure there's the right train, the right holdout. No. We said it'll be due tomorrow. Not everyone gets 100. Make sure you have the right train, that have the right holdout, and all of that right there. Remember, we're doing the Kahoot at 3. Kahoot at 3. Sure. With tree-based models, and so ROC and variable imps is not working. Yeah, we should be able to get the ROC. Do this. You can. Computer stop acting weird. I'm going to restart the computer after this. You should be able to try doing this, Ahmed. Try running this right here on it. No, not that one. Run this one. This right here, run the confusion matrix. I think I did this yesterday. Yeah. So you should be able, I think this gets it out of the support vector machine. Data is not reference. Should be, this was working yesterday, wasn't it? Do we have an R-part model right here? There's the levels. It's nice when code works in the, oh, you see holdout purchase does not have anything in it. Where's the vector holdout purchase? Because it's a different holdout right now. Different holdout. Okay, let's run this. So here I can show this off in the tower here. So the confusion matrix is just one way, and we should have the right holdout at this point. We're running the, everyone gets a 99, 3 p.m. Which question do you have on the homework, Kelsey? What question do you have on the homework? Black Horse has pizza now? Oh, man. Allison, Chelsea and I love, well, this problem is like I don't have my best friend. I don't have Chelsea with me to go and get, no, we love Black Horse. Black Horse is great. Black Horse has really good burgers. They have a good beer cheese. And then they've got the red ale, right? Black Horse has the, what's it called? Black Horse has the red ale, which is amazing. I mean, I think it's okay, but my fiance loves it. So, F2, is that what it's called? Oh, F2, the question. I like fruity. I don't like cider. Like if there's a cider, I'm like, okay, I love cider. So that's cider, raspberry, blueberries. This is the last class. This is it, Jacob. What is that? Manually fit a neural net with the neural net from the. Oh, this is from the. Okay, yeah, yeah. This is from the bonus assignment. From bonus assignment. Yeah, let's do that. Let's fit the bonus assignment neural net from the three. Okay, so one moment. That'll take a moment to do. Oh, there's the param. I changed the params on this. So many random codes right here. Usage. Let's see. I've got the wrong holdouts. This should work. Yeah, it's predicting. Okay, so we're predicting usage. So wait. Object usage not found. Wait, what's going on? Sorry. It's just wrong. I've got so much things going on right here. Sorry. But can you post a link on Canvas for learning data scraping or I'm trying to think if there's a good Ishan, really good question on that. And here, let me hop over to show this real quick. Then we're going to go to Kelsey's question. But the confusion matrix right here, Ahmed, tell me if you're having any success with this right here. The confusion matrix should take your the first argument of confusion matrix, which is a good argument, good function to use right here, is going to be your actual. And then for the take home DOE, you will submit both, submit the knitted file and your RMD. And good question right there, Carly. Oh my gosh, what am I doing? Because this is the predicted. So Ahmed, is this working for you right here to run this function and just put in there your actual and your predicted? So I sent you a file with the data scraping. Yeah, Jordan, I should. You're fine with Austin, Jordan. Jordan, Ishan, send me this out. Sorry, Jordan, I said I was going to do that, and then it's been a busy summer. But my students also here, if you look at the COVID data mining, and I'm going to email him, but right here, you look at what he's done right here. And for some reason, it works on my Mac, but not on this. Yeah, tell me if there's any issues, Ahmed. But this right here, Jordan, do you see the issue with this? I'm literally about to go run and grab my Mac. And, yeah, give me 2 seconds. Because I swear it works on the Mac. Okay, I'm back. You can't see me yet, though. Okay, let's see what's going on with this right here. Gotta love it with 2 computers, and like sometimes I can't see the screen. Oh, it's too bright. I didn't see read HTML in there, but I'm not too well versed with it yet. Yeah, I've done a little web scraping. Let me see this. I'm gonna see if it runs here, because if it runs here, then it should run on the other one. Downloaded. Totally runs. Totally runs. I wonder if you can't see it. I'm like about to walk up to the camera and literally show that it worked on this. It completely works. It has to be. It says error in evaluating. See this right here. It's something with the temp file. See, look, there it is right there, but it's doing it the temp. It has to be. You know what I'm gonna do? Tools. Global options. We're doing it. We're setting the working directory to downloads. There we go. Apply. We're doing it. It's the last day. We're making the working directory downloads. And so let me save this. Okay. Let me close. Don't save. Let me open. Let's see if this fixes it. And let's find out. And then we'll do a little neural nets right here. Okay, let's go back down here. Too many things. Okay, so let's load the... I think I have everything here. I should watch this very carefully to make sure it has everything. Okay, nothing crashed there. Was it my... I have no idea why this is not, because I know it works on trying... See, that's what it says over here. I wish you guys could see the screen. Let me look at all the output I get on this real quick. Let me run each of these in tandem, because I really want to show this off, because this is really good, powerful stuff. Okay, that just downloads, and then that does the trying URL. Yep, same exact thing, and then this works perfectly fine. Yeah, it's like 100%. One of the most frustrating things ever. Go 2 seconds. I'm gonna show this right here. I have no idea. Okay. I really want to get this working because it's really cool. The web scraping is really interesting. And then I'm just like, why is this not working on the PC? And so I can literally show you. Oops, just grab the clock right there. So check this out right here. You can literally see, I got everything. Check it out. This is the code we were running. And so can you see it right there, Jordan? Like it runs perfectly fine. Yeah, let's see right here. We're going to hop back to homework here in a second. And this is blowing my mind because I'm like, I haven't changed anything. It doesn't make sense why it's not working. It works on my Mac. And this is the code we have right here, the TN cases. If you see right here, I'll try to highlight it. This code right here. I have not changed a single thing. And then when I run that right here, I get this. It has to be the way the temp file is being stored. Yeah, so just real briefly on what the code's doing. It's storing destination file temp, read Excel temp. So it stores it as a temp file. Data.url. It's taking that and storing it as destination file temp. Could I change? Let me try this. Let's try this. Temp.xlsx. Okay, cool. Do I have temp.xls? This is... Ooh, wait. I am temp 3. Might be a way it's downloading it. Yeah, it's the way it's downloading it. Yeah, it's the way Windows is storing the temp file. So we isolated the variation and it's coming from this. So when it tries to load, it's storing it as just like a random temp file. And so it downloads it, stores it as a temp file. When this loads, I think it finds the file. It just can't, there's nothing in it. So it's got to be a Windows Mac thing. And literally, once again, it works on my Mac 100%. So I was like, oh, cool, I'll show this to the class. And then, I don't know. Same file, same everything, haven't changed a single thing. Don't know what's going on. Let's hop back over to Alyssa. Allison's asking, can you walk through 3 part B? 3 part B, is this on the bonus assignment? Is this bonus assignment? I'm back on track now. Isn't it, you guys know what it's like when code does not work. You're just like, come on, work. Code, you can do it. It works on one computer, it doesn't work on the other. That's frustrating. It's the same file. It's the same file. That's just I have no idea what's going on with this. So Allison, is it, which question is it? Which one is it, Allison? 3 part B? 3 part B? Is it homework 10, support vector machines and neural nets? Support vector machines and neural nets? Is that the one we're talking about right here? 3 part B. And then I'll be posting. I got a few more keys to post. 3 pod B. Let's see. R can be a Brad. It totally can be. My C models function does not work. What library is that in? That's in reg class. Reg class has C models. It should be reg class. So I think I have library reg class on. Oh no, I reset R. So I do have it on. And then C models, it's C underscore model. So C underscore models is in reg class right there. So you guys are awesome. Let's see this. Okay, 3B. Let's see, what does 3B want us to do right here? Do we have, let's go to the chunk. 3B, bias variance trade-off? Is that right here? Function, right function called n-permanent, okay, cool. Really, Ahmed, wait, so wait, did I put this file up? Is it? It's the same thing, yeah. Ahmed, what do you have working that doesn't work? Like, that's so weird. And I'm sorry. It's just mind-blowing. Just like, what the heck's going on? Why does it work on one, not the other? Who knows? It's a great question. Why does something work on a Mac and not a PC? Maybe Mac went in and edited the PC code to make everything go crazy. Write a function called n-parameter that takes the two arguments, the number of hidden layers, and p returns the number of parameters that have to be estimated when fitting a neural net. Show the output of this right here with the number of hidden layers. Oh, the var imp. Really? Is that it? Is that why it's not working? So the var imp, is that for the support vector machine? Because I was having a hard time. I was like, I know it's worked. So now var imp works on, I don't know. Same code, right? Same code. Okay, let's talk about neural nets real briefly right here, because we have to know how a neural net works right here. So we have to know how a neural net works. A neural net is going to take in x's, which are going to be the parameters in a model. So a neural net is going to have x's, which are going to be parameters in a model. A neural net will then go through hidden layers right here, and the amount of, we'll do a simple one first. The hidden layer will then put an output model out here, and we have to be very careful because we're going to get this output model. Now, we haven't covered this yet, so I have to teach it to understand how we're going to get the number of estimates for the model based on the number of x variables or parameters we have in the model. So each of these are your x variables. These are all x's right here. Now, when they go into this hidden layer, we're going to make a certain amount of nodes in the hidden layer. So I think we have to put nodes in this. Am I going crazy? Because we should have nodes. We'll just put 3 nodes for now because that's going to be easier to calculate. So let's put 3 nodes inside this hidden layer. We have 3 nodes inside this hidden layer. And from this, each of these create estimates for each of these models. So these are your x's, as in this is x1, this is x2, this is x3, and this is x4. But as with, you got it, Kelsey, you got it. Sorry, I jumped around here. As with every single model doesn't just have x's in it, it must have a what. Just go back to a regression. Every single model doesn't have just x's in it. Every single model has a what in it. Like we have our x's and then we have our what. Like you'll have x this, like coefficient x, but there's one thing without an x. What is the one thing without an x? It's known as the what in regression. One thing we have that does not have an x to it is going to be what? Every model has like something first, and then it has like b1 x1 plus b2 x2 plus b3 x3. Every model has it has a starting off point. It has something not related to the x's. Every model has slope and what else? Every model has slope and what else? Every model has a slope and intercept. Yep. So that's the intercept right there. So this right here creates 5 estimates. So because every single one of these will have 5 estimates, like you could switch it up and you could say like, okay, so let me just explain what this is because sometimes I realize you might not know exactly what I've drawn. We're creating here 3 transformed models in this neural net, and it's transforming these x's. It's putting them through a transformation, and it's creating a model. And these are the estimates for the x's contributions to the model. So each one of these is going to create these estimates right here with the intercept and make a model. And what will we do? We will do this same procedure for all of these neurons in the hidden layers. So this right here will have estimates from all those x's, and it'll have an offset. The offset is not related to the x's. And then the next one right here will have estimates from all of these x's, and then it'll have an offset, which is the intercept. I call it the offset, but that's what we call it in neural nets. It's an intercept. It's a thing that is not related to the x's. Now, after we make all of these models, we will then make a model where these kind of become the x's, and they will make the final output right here. Like this is the output. The output of a neural net is right there. And the inputs of a neural net are back here. So the neural net is going to take our x's, make models from them. Whoops, wrong line. The neural net is going to take our x's, make models from them. Literally, it gets pretty complicated here as you draw this. That's why I did it in parts. And just got to do the pattern. Just got to make them all do that. And there's the offset. And then, so we make models from our x's, and then our models make models. Does that make sense why this is kind of called the hidden layer? Because what do people really want to focus in on? Here's my x's, like might be like, like what explains the variation in the calzone, and then here's my output of what is the rating of the calzone. The hidden layer is called a hidden layer because we don't focus on these equations. We focus on the final output of the model, which is like, what is the predicted value of what someone will think of this calzone? And then we focus in on what is the x's that explain the variation in the calzone. We don't look at the models that make our final model, because this is why it's called a hidden layer. Does that make sense why they're called hidden layers? You can do more hidden layers. Who's with me on this right here? And it's like, okay, we're making models that are models then make a model from our model. And they're hidden because you don't look at the kind of step models. So you kind of use your models as new x's. So these are kind of new x's for the final model. They're not really x's. Don't say Brian told you that those are x's, but like pseudo new x's, like kind of. I want to put like they're kind of new x's for the model, because you're going to make your final model from models. It's models making models. It's models on top of models on top of models on top of models. Because what you can do is you can create a neural net with a deep learning neural net. And we've covered most of the notes by talking about this. You could have a deep learning neural net, and this would just be crazy if I drew out how this works. I could show the notes on it. But a deep learning neural net could have like 3 hidden layers, and you could even have 2 outputs. You could have like 2 different outputs, like it could give 2 different y values. It's pretty crazy what you can do with these things. Just do 1 because that's going to get more confusing. Good. If I drew this out on all the things right here, it would be absolutely insane how many estimates we are getting. And then literally you'd have to draw this one. Oops, wrong arrow. I'm not going to draw this all out, but you would literally draw all the connections between all of these, and then finally all of these models would make estimates for this as you went through all of the massive amounts of hidden layers and connections between them. And we should have the picture up because that's going to be the easiest way for me to show you visually what's going on here. Let's just show I had it open a few days ago. I think search neural nets. Wait, what? We showed it. There we go. There we go. What? Clicked it. Am I going crazy? Wait. There we go. And there's a neural net. And here's a deep learning neural net. So here's the deep learning neural net right here. Let's hop to the main screen for a second. So this is a deep learning neural net right here with tons of hidden layers, and it just gets insane to draw it all out. So this sets us up for success on how to do this right here. Is we need to see what we want. Write a function called the number of parameters that takes 2 arguments, the number of hidden layers, and p, and returns the number of parameters that have to be estimated when a neural net is fit. Show the output. Okay, so the number of hidden layers that we use to model is a choice. As we increase the number of hidden layers, what happens to the bias? Cool. Yeah, it's going to overfit towards it. There we go. In other words, it walks you through everything right here. So right here, if hidden layers is the number of neurons and hidden, that's the number of neurons in each hidden layer, is the number of neurons in a single hidden layer of a neural net, and P is the number of predictor values to develop a formula that relates to that. Cool. Okay. So the best way to do this, to figure out the number of predictors or estimates we are making, is going to be to kind of use an example we've already created. So using this example right here, because we have the number of neurons in a hidden layer, we should see in our example problem that we first drew, we had how many neurons in this hidden layer? We had how many neurons in this hidden layer? How many neurons do we have in this hidden layer right here? How many neurons do I have in my hidden layer? Who knows? Who is here and knows how many neurons are in this hidden layer? 1,000 points, who knows? How many neurons are in this hidden layer of this neural net? How many neurons are in this hidden layer of the neural net? How many neurons? We're still broadcasting, right? 3, you're right, Jordan. Yep. You got 1, 2, 3. There's the 3 neurons in the hidden layer. So this is a neuron. Remember, this is not on the test, luckily, so don't worry too much. There's a neuron here. There's a neuron here. There's a neuron here. There are 4 predictors. Does everyone see these are your 4 predictors? These are the 3 neurons. Does anyone know how many estimates there are? How many estimates are created? And I have to pause and think. I think I know how many estimates are created. How many estimates are created? Any guesses on how many estimates? 10,000 points if you get it right. I've got it drawn out, and I'll check my answer if you give a different one. I'll give this but think about this. How many estimates are being created to figure out this neural net right here? And then we have to mathematically write this out. So we can use our numbers then. And this is a pretty tough question. The answer is, give it like 5 seconds. 5, 4, 3, 2, 1. The answer is a lot. Like, Carly, you get the 10,000. I'll take that right there. That's worth it. I mean, it's just fun day. Giving out crazy points. Just, I don't know. Breaking the point system. Always do that. And I shouldn't. So there's 19, I believe. There's 19. The reason being is because each of these make 4 estimates here with the offset. That's 5. Each of these make 4 with the 5. Each of these make 4 with the 5. 5 plus 5 plus 5 is 15. 1, 2, 3, 4, 19. So there's 19 total lines that I've drawn on here. There are 15, I think that's right, 15 red lines, 12 from here and 3 from here, 15 total red lines. And then there's the green lines total up to 4, 3 from here and 1 from here, that's 19. So every time I try to check this, I'm getting 19 as I do this. You can do a really simple neural net. Here's the most simple of neural nets I can do. Can anyone tell me how many estimates in this right here, how many estimates will this create? I'm thinking. Oh, I got it. I think I got it. So this is 2 predictors, 2 neurons in the hidden layer. So here's your 2 predictors. So this would be P equals 2 and N hidden equals 2. So there's 2 neurons in the hidden layer. And this is where people get confused because every time you do this, you have to make an offset right here. So you have to do an offset for the model. And this is the answer to the question. Oh, I was off by 1. It's 9. So there are 9 parameter estimates being created. So there are 9 parameter estimates being created. Somehow I got 8 in my head, and then drawing it out, I was able to see it's 9. So we've got a few answers already because this answer needs to come out to 9. So that has to be 9. We know that. We just drew it out. Our drawing should be accurate. The answer is 9. This one right here, when we look at the P is the number of predictors. Sure, space pen. There's 4, and then the N hidden is equal to 3, and then the answer should be 19. So we should get right here 19 when we do this. So now we have to think about how to do this. We have to be like, okay, how do we do this mathematically? Well, when we look at each predictor will add, when we look at each, let me think of the white ray. Each neuron here will have 1 plus the amount of predictors. So you see each neuron is going to have 1 plus the amount of predictors. So when we look at P equals, let's say, 2. And then we need to go here and go to N hidden. N hidden, let's go to 2. Oh my gosh, what am I doing? And let's think about this. So what we need to do is we need to do P plus 1. Because what am I doing by doing P plus 1? Let's look at this. P plus 1 is me figuring out this right here. What do I mean? Like, I can see it, but I want you to see it. P plus 1 is me figuring out this right here. That's P plus 1. That's P plus 1. That'll always solve for how many estimates are going into each layer of the hidden, each neuron of the hidden layer. But then I need to take P plus 1 and times it by what? I need to take P plus 1 and times it by what? P plus 1 and times it by what? Who knows? P plus 1 and times it by what? And the answer is right here. And do P plus 1 and times it by what? For this model right here. Times it by 2, which is the number of hidden layers. So now we do P plus 1 times the number of hidden layers. So that will get us 6. And what does this 6 represent? The 6 we have right here represents 1, 2, 3, 4, 5, 6. That's what it represents right there. It represents 6. We can also check our other problem right now. If we go back to the previous problem, we said with this right here, there should be 15, and that's 4 and 3. So we should get 15 with 4 and 3. So let's put 4 predictors, 3 right here. We should get 15. We get 15. So now we have checks. We've drawn it out, and we're checking, and we're making sure we're doing it correct mathematically. And now we just need the last part. Because now for the last part, we just have to add to it this. Well, this is going to be how many plus what? Look at this right here. How many lines do we have right here? And there's hints. How many lines? Who knows what math we will add to it? We'll go what we just found plus this. How many will we have right here? What is the amount of lines we have at the end right here? Well, you can count them, but what is it mathematically? Who knows what the amount of lines here that we have at the very end of this graphic, how many lines do we have mathematically? It's the amount of, who knows? It's going to be the number of neurons in the hidden layer plus what? Plus 1. So what we should get right here, if I did the plus, which I didn't do, we get 19. And 19 was the answer when we had 4 and 3, and we should get here 9. Oh, didn't click them all. And there's the 9. So we have confirmed right now that this works. And guess what? That's the formula, basically. This is the function we need, because it says, that's not the answer, obviously. Write a function called the number of parameters. So let's go right here, where it takes, we're just going to go to return right here. Return this. And now we go here, and we want P. And is that right? It says the P is the first thing. No, I think N hidden. Oh, it doesn't matter because it'll do it either way. No, he just has to make sure because they're not saying what he thinks. Show the output of write a function call and takes 2 arguments, N hidden. Okay, so we should do it in that order. So be very careful. Yeah, I think that's right. And let's test out our function real quick right here because we had 2 and 2. This should give 9. That does. Don't want to change what it is. And then we had, what was it? What was the other graphic? 4 parameters and 3 in the hidden. So 4 and 3, and this should give 19. Yep, okay, it's working. And there we go. There you go. Wow, that neural net is probably going to be overfit. Does that help right there? I think we have, and then we have F2. Let's see here, F2. Here's F2. Manually fit the neural net right here. So let's take a look. I'm going to take quickly over here. We're going to manually fit a neural net. Woof. Manually fitting the neural net is pretty crazy. So let's take a look right here. Let's jump into this. Manually fit the neural net. Cool. So we're going to use the neural net library here. I'm just going to take the code over here. Let's drop it in and let's do it. So do I have neural net on this computer? Once again, update this computer. Nope, didn't think I had neural net. And let's go here, install.packages. Do not leave the install.packages ever in here because you cannot knit with an install package. And everything, we need to click yes. And is it going to work? Restarting. Let's look through the code. We'll look through the code here in a second. Okay, it worked. And let's take a look at the neural net right here in just a second. Let's clean up our code, make it look all nice. Got the Y variables. There's there. I think we can we do it through the tilde? I think we can. Let's find out the hard way if we can do it through the tilde. We will find out. I don't like how that, we'll put this to a new line. Everyone knows we like nice looking code. So many spaces. There we go, that's better. And it's much better to see the code when it's not all crazy like. Oh, it's because of this. Really? There we go. I think I'm good with that, and I think it'll work. It's got the append. Let's take the append off there. Could not find function neural net. Library neural net. Warning message, cool. Object train not found. We need the train data. Let me go grab the train data from when it was made. Let's go grab the train data. The train data was made. Train.rows. What are we training on? Here we go. Which variable are we training on? Where did we make our train data? Oh, I don't think I've loaded it in because it's already in the environment. So let's go to, I downloaded it. So let's go to, use it right here. Cool. And that should do it. And let's take a look. There we go. Cool. We got it. Let's take a look at the code. How are people doing right here? So with this neural net right here, we're doing sale price, and that's what we're predicting as the Y. We're doing the overall quality, the GRL live area, total BMSST, and garage cars. We're looking at the data train. We have three hidden, we have three nodes in the hidden layer, and we have the linear output true. Let's plot this neural net. We're going to need a bigger window for this. And that should, I think I'm still on the line. Good, awesome. There's our three nodes in the hidden layer. Okay. So this is what we were drawing out literally moments ago. So this graphic right here is the visualization we were doing right over here and here. So if you look at these graphics right here, we get the same sort of output from R, and we can look at some of the questions, but specifically looking at the format of the code, once again, I just want to point to the similarities between what we've been doing. So where is it? Where are you at? So with the code, let's take a look. So many things. So we've got here neural net y tilde x comma data equals hidden and linear output. Could you post like, sure, let's do it. And then you just plot it. Yours is not running. Here, I'm going to take everything but the last two arguments. And then this. And make sure you have the assignment data loaded. You have the data loaded for the assignment. And it's y tilde x comma data equals comma hidden and then linear output. So a lot of things follow the y tilde x comma data equals format. So if you look, it's kind of the classic y tilde x comma data equals. Like I literally have everyone repeating that in 320, y tilde x comma data equals. So there's your y tilde x comma data equals. And then we do hidden layers. So you can change it. You're like, why not change it? So let's go here and change it to hidden layers 5, just for the fun of it. It didn't break. And then you can see the output right here. Now this is a totally different model, but you can see there's 5 neurons right here. And you're just going to plot the object it creates. You're going to plot the neural net. You're welcome, Kelsey. No, I appreciate you guys working on this. That's why we're here to talk about it, talk about the theory. Sometimes the code can just literally be what drives you mad. The code can be the what's going on, why is this not working, something's not working. See, now it's not even going to the plot window. I wonder why it's not. Who knows? So when we look at what does 3F ask us about? What does 3F ask us about? F2. Does not ask any questions to interpret it or to write out the equations. So, yep. There should be a response. Does it want you to write? So the coefficients should be this, this, this. Yeah, there's the 2.52 right there. So, and the 1.27 is right there. It's a little hard to see, but yeah, depending on your computer, configure, sanity check, Wait, and then we should write an equation, right? Provide a plot of this neural net and report the equation for the weighted sum of these predictor variables plus that is being fed in the topmost neuron. Okay, so we have to write out the equation for the topmost neuron. And to do this, it's just writing regression again. All this is writing regression. I love these questions on the test, but they're not on the test. So when you look at this right here, what is the intercept of the top neuron right here? What is the intercept of the top neuron? So here, I'll start writing in the chat right now. What is the intercept of the top neuron? I think we were predicting, price was it? What variable were we predicting again? We were predicting, gotta go back to here. Sale price, yeah, it was price. We are predicting sale price. What is the intercept of the top neuron? What is the intercept of the top neuron? I'm gonna abbreviate it. What is the intercept of the top neuron? Anyone know the intercept of the top neuron? What is the intercept of the top neuron? The intercept of the top neuron would be... Shouldn't yawn on the camera. 2.52. The intercept of the top neuron would be 2.52, and I'm obtaining that from right here. This is the top neuron in the hidden layer. And then what is the coefficient of overall quality? Well, the coefficient of overall quality is 1.27, and then we would just do like overall quality. So overall quality. And you might see the pattern right here because all you're going to do is sale price equals this plus this times this plus this times this plus, really hard to see, but it's this times this plus this times this. That one is the top one because this is the second one. Does that make sense right there, Kelsey, how to write the equation? That the top neuron has this intercept plus this times this plus this times this plus this times this plus this times this. It's literally almost identical. If a 320 student was in here, I'd be like, okay, remember how we do, if we're making a linear model, we predict height from weight and GPA, and we do data equals survey 11. If I still have it open, I do 10. And then we go to the summary of the model right here. And all we do to write the model is we do intercept plus this times this plus this times this. Does that make sense right here? Because you're just doing the same thing. You're saying you do intercept plus this times this plus this times this plus this times this, the number that's associated that goes into that, plus this times this. And it's the same thing as the models we're making here where we do intercept plus this times this plus this times this. That's why I really like a lot of these topics just converge. And it's like, how do you write these equations? It's just taking the intercept. It's just taking the estimates for the model. Do you think you have this one done, Kelsey? Any more questions? Who's got questions? I need that second Red Bull. I still got some more coffee. I'm running low on coffee, Red Bull. Oh, man. Awesome stuff. Great work, everybody. I'll send out reminders. The Kahoot will be starting up. You're welcome, Kelsey, of course. No, thank you for asking. Thank you for working on the bonus assignment. Thank you for learning about neural nets. And the craziest thing, yeah, no, Amit, feel free to ask. The crazy thing is just how easy coding makes things. But then literally something doesn't work in code and it's like, oh my gosh, the world's, I just want to know why this COVID thing is not working. Because it's so cool. John made such awesome code. And I'm like, why is it not working on the PC? It works on the Mac. I need to look into this error right here. I'm like, why are you downloading this data set 1 billion times from us? It's when it downloads it. Let me go to this website. Let me look. That downloads it. That literally downloads it. That just downloaded it. What is download not file? File not doing it. It has a different default on like a PC or something. Why would it have that? Why would it work differently? Why would it work differently on a PC? It literally just downloaded the file when I loaded the link. Why would it not work? This downloads the file. This gives it the destination name. So that has that. Mode, okay, download. Why would it not do that? And it downloads to temp. And it even tells me when I download it here, content type, download. See, then we give it a name. Temp COVID. See what that does. See, it's a file. Is it 19 kilobytes? Yeah, I have no idea how to open this. Well, you see, that doesn't look right. That looks like something happened. When we compare models at the end, do we take the best model and see if the second best is within one standard deviation of the next? When you're doing the validation, what I mean is we compare two at a time. Well, you kind of like do like a round robin of it where everything compares against each other. You could kind of do this. Like imagine you're playing like a video game and your friend walks in the room and is like, I can beat you at this video game. And then you go against them and then the winner continues on. So, and then another person walks in the room, they're like, I can beat that person. So then they get to go against them and the winner continues on. So you are always kind of, as I do it, like when I make models, is I kind of like make a model and I'm like, okay, this is how good it does. And then I make the next one. I'm like, oh, okay, this one did better. Okay, that's the new winner. And you kind of just, you can make a list of them at the end. A lot of people will make a list of their models and there's like some clear winners and clear losers when you look at the different models. So you can make a list of your models and compare all of them at the end and kind of maybe say which models are within one standard deviation. Like you can make a list of models and be like, here's my top tier models, here's my lower tier models. And then if models are within one standard deviation of each other and you usually just compare a 2x2 model, you can maybe compare 3 models, but you would take the highest of the standard deviation of all 3 of them. But I usually do like pairings of models to be like, okay, between these 2 models, this one appears to be better. And yeah, it's a really good question, Ahmed. Really good question. I'm going to try to figure out what's going on with this Excel data. But 3 p.m. Kahoot. 3 p.m. Kahoot. I will see everyone then. So bye, everyone, for now. We got to end. We got to end with Jason. We got to do it. One more time. Ending with Jason right here. We're doing it. 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.